the Federation of Astronomical Societies organising today's webinar. And some of you may not know what the FAS is. We were founded in 1974 as a collaboration of like-minded societies, mostly based in the UK, but we do have members in the Channel Islands, the Isle of Man, Gibraltar, and Costa Blanca in Spain. We have about 200 member societies altogether, although we're still going through the renewal process this year, so that number's climbing, and represent about 12 to 13,000 individual amateur astronomers who are the members of those 200 plus member societies. We work on the principle that we provide guidance to those societies, guidance in the form of policy documents, of code of conduct, health and safety, doing risk assessments, those sorts of things, laser safety, laser pointer safety. And we also offer, and have done for some years, we arrange a low-cost public liability insurance so that astronomical societies are covered when they do outreach to the public. Okay, we have members, as you can see, scattered throughout most of the UK. Some of our very largest societies have 400 or 500 members, but as you can see here from the graph, the median number is about 40 members, which gives you a typical size for societies around the UK. Okay, so that's enough about the FAS, and I will now hand back to Jerry to introduce the rest of the meeting, and I'll see you again towards the end of the day. Thank you. Over to you, Jerry.
We've had our welcome from Paul Daniels, the president, and after this quick run through, session 1 is going to start off with our first speaker, Lord Martin Rees, the Astronomer Royal, followed by Greg Smye-Rumsby. We're then going to have a 10-minute break, but if you come back after 5 minutes, then we'll have a little slideshow for you. That'll be followed by presentations from our 3 sponsors. Then session 2 will start with Nick Szymanek, followed by George Tahu. After each speaker, there will be short time for questions. If you go to the Q&A option on the Zoom menu, then we invite you to submit your questions, and we will go through those after each speaker. Then at the end, we'll have a quick roundup, and the president will say something more about FAS events. So I'd like you to welcome our first speaker, no less an authority than the Astronomer Royal, Lord Martin Rees, who is, well, I don't need to say well known to all of you. We are absolutely delighted for him to be our first speaker today. Well known for various appearances, lots of books, including Just 6 Questions, and his subject, or the title of his subject today, is From Mars to the Multiverse, although he did say to me that he may not get beyond our own galaxy. So, Lord Rees, over to you.
Right. Well, thank you very much, Jerry, and hello, everyone. Can you hear me?
Yes, we can hear you.
Okay,
we can hear you.
And I will now try and share my screen.
We've got that, yes.
Okay, and I now have to go to right. Okay. Sorry, it's, here we are. Yep, good. Well, this is indeed my title, and as Jerry said, we'll see how far I get. But I thought I'd start off by asking why we do astronomy. I'm asked this a lot since it's my job, as it were. And I would say four things. It's to find out what's out there, cosmic exploration, and to try and make sense of what we find there, using the laws of physics and perhaps some new ones. But then we want to try and do what Darwin did for life on Earth, the entire universe, to ask how it evolved from a simple beginning to its present complexity with stars, planets, and people. And then, of course, some of us want to get a bit closer to philosophy and to understand at a deeper level, why is the universe the way it is? I'm going to start with a bit of history. This is Trinity College, Cambridge, which is where I work. And it looks the same now as it did 3.5 centuries ago. And that's when we had our best ever student. And here, Isaac Newton. And in fact, legend has it that he had his great idea about the universal law of gravity when the university was closed in a plague year of 1665, and he was under the apple tree, or so we are told. Well, the university wasn't closed again until this year, and lots of our students have been at home, and I just hope some of them will have some equally great insights, as Newton did while they sit in their own gardens, although I'm not holding my breath for that. But what about Newton? He built his telescope. This is a replica in the Royal Society of his 4-inch telescope. But he also thought about space travel. This is a famous illustration from the English version of Principia. It shows, as you can see, cannonballs being fired from a mountaintop. And if they're fired fast enough, then they go into a circular orbit. And this is still, I think, the easiest way to explain to people the concept of orbital flight. Well, he calculated that in order to go into this circular orbit and not hit the Earth beforehand, the cannon has to fire at 18,000 miles an hour. Far beyond, of course, what was possible at the time. And as everyone knows, it wasn't until 1957 that the Soviet Sputnik became the first object to achieve orbit. This was followed by some dogs and then by Yuri Gagarin. There he is. And incidentally, Yuri Gagarin came to London and was mobbed by large crowds, but the then Prime Minister, Harry Macmillan, who was a rather cynical gentleman, said it would have been twice as bad if they'd sent the dog. So after this, we had, 7 years later, we had this iconic picture for environmentalists, Earthrise, taken from Apollo 7. And then, of course, we had the moon landings. And I treasure this picture signed for me just a few years ago by 7 of the Apollo astronauts. And of course, Neil Armstrong's one small step was in 1969. And of course, since that time, no one's been back to the moon. You've got to be middle-aged to remember when men walked on the moon. And to my students, it's ancient history. They know the Egyptians built pyramids. They know the Americans went to the moon, but they were both motivated by rather strange national goals. But of course, we know very well that space affects us every day through navigation, communication, sat-nav, and all the rest of it. And also we know that uncrewed spacecraft have been and given us close-up pictures of all the bodies of our solar system. So let me give you a very quick tour. If you're launched off into space and going outwards from the Earth, then if you look back from, say, 10 million miles, you see something like this. This shows the Earth and the Moon with the sun coming from the right-hand side. You see something like that. And then you would get to the red planet, and we're going to have a whole talk from George Johu about the latest on that. So I'm going to say very little about Mars, but this is a picture which shows the Curiosity probe, which was sent about 10 years ago. And of course, we've had the wonderful or more sophisticated Perseverance, which we'll hear about later today. But going further out, here's Jupiter. And this was taken by Juno, an American probe, which shows the weather near the North Pole of Jupiter. And these are lots of complicated cyclones. And of course, there are lots and lots of wonderful pictures like this. And of course, we've had close-ups of the moons of Jupiter. These are the 4 classical ones found by Galileo. And of course, we know they're very different. I mean, Europa, for instance, is covered in ice, and Io is sulfurous and volcanic. Going further out, this is a wonderful Cassini probe, which spent 13 years orbiting around Saturn and getting close-ups of some of its moons. And it sent back this rather nice picture, which shows an eclipse of the sun by Saturn. It was lined up at a distance behind Saturn, such that Saturn just covered the sun, and you can see the rings of Saturn in sunlight, whereas the planet itself is blocked out. And you can't quite see it, but the Earth is at the end of that arrow taken on this picture. Cassini carried in its cargo bay a European a probe called Huygens, which landed on Titan, the moon of Saturn. And this is a picture of Titan. It looks rather nice, little lakes and rivers, but the temperature is minus 160 degrees centigrade, and these lakes are liquid methane or ethane. So not a very salubrious place, and any life there would have to be not water-based at all. And this is Enceladus, a smaller moon of Saturn, and this has an icy cover, and we have good evidence there is water underneath that because it's seen to be spraying out. And we wonder, could there be any creatures swimming down under this ice? This is a much smaller moon. And we had a few years ago from NASA's New Horizons this close-up picture and several close-up pictures of Pluto. This is remarkable technology. And it's remarkable because Pluto is about 12,000 times further away than the moon. And the probe that went to Pluto, and indeed Cassini, they took up to 10 years on their journey to their destination, and of course 10 years in the planning stage. So they are all based on 1990s technology. And if we think how our smartphones have improved in these 20 years, we can imagine how much better one could do today, starting from scratch to design a probe to the outer planets. And this is something we should try and do. And I can well imagine that there will be flotillas of small spacecraft which will be sent to explore all the outer planets and their moons. Well, what about humans? As we know, it's more than nearly 60 years since Schmidt and Kernan returned from the last Apollo trip to the moon. No one since then has been beyond low Earth orbit, mainly in the International Space Station. Not very glamorous or dramatic. In fact, a space station only gets public interest when something goes wrong, when the loo fails or something like that, or when Chris Hadfield, the Canadian astronaut, sang David Bowie songs to a guitar accompaniment. That sort of thing makes the news. The science wasn't really very spectacular. But that has given hundreds of people the opportunity to go into low Earth orbit. And the question is, when will humans return? As we know, there are plans to send humans back to the moon within 5 years, whether that will happen. And there is, of course, talk about sending humans back to Mars, perhaps in the next 20 years. I must say I'm rather ambivalent about these plans, because the practical case for sending people is getting weaker as miniaturization gets better and as robots get better. It's true that curiosity and even perseverance won't be able to do as well as a human geologist, but AI is developing fast, so one day they will. And so, to be honest, if I was an American, I wouldn't support the human spaceflight program. I would leave it to the privately funded companies like Elon Musk's SpaceX and Jeff Bezos' Blue Origin. Not only are they doing a good job, but the most important point is that they can be less risk averse. The trouble with NASA doing something is that they've got, when they're sending civilians into space, to be very cautious. And of course, we know that the shuttle was launched 135 times, and it had 2 spectacular disasters, which I'm sure most people in the audience above a certain age can remember. Each of those was a national trauma, which held up the program for 2 or 3 years as they tried to reduce the risks even lower. But 2 failures out of 135, that's less than 2%. And test pilots and many astronauts are prepared to accept that risk, as are those people who do extreme sports. So my take is that the first people who should go to Mars will be people accepting a very high risk, maybe even a one-way ticket, who are the kind of people like Sir Ranulph Fiennes, who dragged a sledge across the Antarctic in winter and things like that. People like that, prepared to take the risks. And they can, of course, go on a more risky and therefore much lower priced venture. So I think that since manned spaceflight is just an adventure, it's got no practical use now. It should be used for that. Incidentally, I don't entirely agree with Elon Musk. I admire him greatly. I think he's a 21st century Brunel. He's done wonderful things. But I don't agree with the view espoused by him and by my late colleague Stephen Hawking that we should envisage mass emigration to Mars. You know, millions of people going and trying to live there in conditions that are acceptable to ordinary people. I think that's a dangerous delusion. I think the Earth problems have to be solved here on Earth. Dealing with climate change is a challenge, but it's complete doddle compared to terraforming Mars and making Mars habitable. So I don't think we should expect ordinary people en masse to go to Mars. We shouldn't encourage it. It's worse than living at the South Pole, at the top of Everest, or on the ocean bed. And no one really wants to spend a long time doing any of those things. But nonetheless, I think we should cheer on the space adventurers, and I hope there will be some who will be on Mars by the end of the century. And the reason for that is that they will be ill-adapted to being on Mars. The atmosphere is wrong, the gravity is wrong, etc. And they will use all the technology of cyborg and genetic modification, which we will then have by the end of the century, to adapt themselves to an alien environment. Those technologies are going to be, one hopes, regulated here on Earth, but these adventurers will be away from the regulators. And of course, we've evolved to be adapted to the Earth. We have no incentive, whereas they have a big incentive. And so they and their progeny will evolve in a few centuries at most into a different species. And of course, they may become electronic. And if so, then they may be near immortal. So interstellar voyages will be no deterrent to them. So I think in the future of intelligence, these people on Mars will be great pioneers, and they play a historic role. But as I say, I think Mars is a place for adventurers who are prepared to have one-way tickets. And Elon Musk himself has said that he hopes to die on Mars, but not on impact. And good luck to him. He's, I think, only 49 now, so 40 years from now, he may be able to do this. Well, as I say, the remote descendants of these Martian pioneers may, of course, and they do in the view of some science fiction writers, spread through our galaxy, spread far beyond the sun to other systems. And of course, this therefore means that even if life is now unique to the Earth, then it may, in the far future, spread more widely. Of course, as an astronomer royal, I get lots of letters from people who say, why are you talking about aliens not existing? They're people who've been visited by the aliens, abducted by the aliens, etc. And I get letters from these people and I say, do you really think that if the aliens had made a huge effort to traverse interstellar space, would they just meet one or two well-known cranks, maybe make a corn circle and go away again? It seems unlikely to me. And I tell these people to write to each other and not write to me. But nonetheless, the question of life elsewhere in space is one of the most important in the whole of science. So let me say a bit more about it. Of course, as we know, they'll be looking on Mars, and one hopes that in the next decade or two, one will be looking on Europa and Enceladus and other places like that for evidence of life. But of course, what really transforms this whole scenario is the realization, which we've had for the last 20, 25 years, that most of the stars in the sky are orbited by retinues of planets, just as the sun is orbited by the Earth and the other familiar planets. And this first one was discovered in 1995 by two people then in Switzerland. And this is Didier Queloz. This is the day he won the Nobel Prize for discovering the first planet just last year. He's discovered many hundreds of planets since then, and he's now one of my colleagues here in Cambridge. You've got really great and enthusiastic man who's got great achievements ahead of him as well as behind him. And the way these planets are discovered, there are two ways. The way he discovered his first planet was by observing a star very carefully and observing the small change in its Doppler shift due to its small circular motion. Because if a big planet is going around a star, then both planet and star orbit around their center of mass, the barycenter, and the star goes in a little orbit. And if you can measure Doppler effects down to a few tens of meters per second, you can detect this evidence. But most of the planets have been detected in another method, by detecting transits. The point here is that if a planet moves across the face of a star, then if you're doing photometry of the star, then the star will get slightly dimmer because part of its light is being blocked out by the planet. For instance, if you're looking at the Earth and the sun from a great distance, then the sun will get fainter by 1 part in 10,000 when the Earth moved across it, because the Earth is about 1% of the diameter, so 1/10,000th of the area of the sun. And so this is a way in which you can infer the size of a planet from the depth of the dip, and also the length of the planet's year from how long it takes between successive dips. And literally thousands of planets have been discovered by this method, and most of them by NASA's Kepler mission, which looked for 3 or 4 years at an area of sky about 7 degrees across and measured the brightness of 150,000 stars in that part of the sky with a precision of 1 part in 10 to the 5th, looking for cases when there were regular dips. And they found many, many thousands of these things. This is a rather busy slide, but the bottom left shows a rather silly way of presenting some of these, where the size of the dot measures the size of the planets in the period. But the main point is that there are many thousands of these planets which have been discovered around the stars. Well, we'd really like to be able to observe the planets rather than their shadows. And as I said, most of the discoveries have been either looking at the effect on the star's motion, causing it to wobble, or on the star's brightness. So we see the indirect evidence of the planet from how it affects the star that we can observe. It's very hard to detect the planets. To indicate just how hard, let's imagine that there were some aliens out there looking at the solar system. If they were, say, 50 light years away, the sun would look an ordinary star, and the Earth would look, in Carl Sagan's nice phrase, a pale blue dot, a billion times fainter than its star, our sun, and very close to it in the sky. You're looking, as it were, for a firefly next to a searchlight. But supposing the aliens had a big telescope and they could observe the pale blue dot, then they could learn quite a bit about it, because the shade of blue would be slightly different depending on whether the landmass of Asia or the Pacific Ocean was facing them. So they could infer that there were continents and oceans, they could infer the length of the day, and by taking spectra of the light, they could learn something about the atmosphere of the planet, whether there's oxygen in it, etc. And indeed, if they took the spectrum, then they could detect vegetation, because chlorophyll has a distinctive effect on the red edge of the spectrum. And at the moment, we don't have telescopes that are powerful enough to do this. But James Webb Space Telescope may do some, but more important, this telescope here, which is the European Southern Observatory's ELT, extremely large telescope. They're not very imaginative in their nomenclature. This telescope, which has a 39-meter diameter mirror, not one sheet of glass, but a mosaic of 800 sheets of glass, this will be able to collect enough light to be able to detect planets, even just Earth-like planets, around nearby stars. And when fitted with a high-resolution spectrograph, which is funded and is now being constructed, they will be able to separate out the light and the spectral contribution from a planet, from the much, much bigger spectral features from the star itself. They can separate them out because we know what phase in its orbit the planet is, and of course that gives a changing planetary contribution to the spectrum. So one can separate out the planet's contribution. And one of the most exciting results from this telescope in the next decade probably will be a crude spectra of some nearby Earth-like planets. That'll be very, very exciting. But is there going to be life on these planets? One thing we have learned through data already, from looking at samples of stars, is that almost every star has planets around it, and 1 in 6 stars, that's a rough guess anyway, has an Earth-like planet, a planet about the size of the Earth, at a distance from its parent star, such that water can exist, neither boiling away nor staying perpetually frozen. This is the so-called habitable zone. And if we're looking for life, then of course we should be open-minded what it's like, but the best way to start would be to look for life on a planet which is rather like we think the young Earth was. But of course we don't know how likely it is, because some people are surprised when they're told that although we understand Darwinian evolution from simple organisms to present day ones, we don't understand the actual origin of life, the transition from complex chemicals to the first metabolizing, reproducing things that we would call alive. We don't understand that yet. And we therefore don't know whether it was a rare fluke, which only happened here on Earth, or whether it's something which would happen in any Earth-like habitat and therefore widespread. So this is why it's a fascinating question. And I'd just like to put in a bit of sort of modesty on behalf of astronomers and physical scientists here, because everyone says, isn't it hard to understand stars and galaxies and all that? And the point I like to make is that a star or galaxy is very simple compared to even the smallest insect. The challenge of understanding the layer upon layer of complexity in the smallest living thing is in a sense greater than understanding stars or galaxies. And some of you may recognize this picture. It's a flea, and this is from a book published in the 1660s by the Royal Society called Micrographia by Robert Hooke, who was in fact Newton's least favorite colleague in the Royal Society, but he had one of the first microscopes and he drew very well. And of course, this was a flea. And of course, before his time, no one had any idea that a flea was as complicated as this, and now we know far more about it. So exobiology, which is now, in a sense, a serious part of astronomy, is going to be a very, very complicated but fascinating subject. Well, I won't go any more about that. Let me go back to the relative simplicities of the inanimate world and talk about the lives and deaths of stars and galaxies. We know that stars are forming in places like this, the Eagle Nebula. And we know that they end their lives when they run out of fuel. And we know the sun will end its life in about 6 billion years. It's less than halfway through its life. And then it will look something like this. It'll blow off its outer layers to make a planetary nebula and leave behind a white dwarf star. We also know, though, that heavier stars than the sun live their lives faster, they burn the nuclear fuel more quickly, and they die in a more spectacular way to give supernova explosions. And of course, everyone here knows this object. This is the Crab Nebula, which is the remnant of a star which exploded nearly 1,000 years ago in the year 1054 AD. And if anyone reads Chinese, this is the record of the Chinese court astronomer, I guess the counterpart of the Astronomer Royal, who reported to the emperor that a guest star had appeared and become brighter than the moon and faded after a few weeks. And in that part of the sky, we now see the Crab Nebula. Here it is. Well, objects like that might seem far away and irrelevant to us, but of course we now know that we wouldn't be here if it wasn't for these supernova explosions. This is the reason. If you were to take a slice through a big star, say 10 or 20 solar masses, towards the end of its life, when it's running out of nuclear fuel, it'll have this sort of onion skin structure. It'll have hydrogen and helium on the outside, and then it'll have carbon and oxygen, and then deeper down, it'll be processed by more nuclear fusion further up the periodic table, and you get to iron in the middle. And when the star has its final energy crisis, it blows out all this stuff, this debris, into the interstellar medium, looking like the Crab Nebula, but then eventually that will merge with the interstellar gas and looks somewhere like this. And then eventually new stars will form, but they will form from gas which is not just pristine hydrogen and helium, but is contaminated by the debris from the earlier generations of stars. And so we now have the wonderful story that every atom in our bodies was in a star which lived and died before our solar system formed. And indeed, we have atoms that originated probably in many hundreds of different stars across the Milky Way. And the people responsible for this wonderful vision are mainly these people here. This is a picture of Margaret and Geoffrey Burbidge, Willie Fowler and Fred Hoyle. In the 1950s, they wrote a classic paper, which is normally known by astronomers as B²FH, after the initials of the four authors, where they codified these processes, and they showed that this could help them to understand why there was a lot of oxygen and carbon and not much uranium or gold, and how they came to be in our solar system. So in other words, that we are stardust, or if you're less romantic, we're the nuclear waste from the fuel that made stars shine. And so their vision, oh yes, let me show you this picture. Margaret Burbidge, she died last year, aged 100. And this is a picture of her with a birthday card on her 100th birthday. She had a wonderful life and was, she started out in the 1930s at University College London at the Mill Hill Observatory, where she worked during the war, and she kept going until just last year. I should have said that the earlier picture was taken in 1971 on Willie Fowler's 60th birthday. He was a great lover of model trains, and that was our present to him back in 1971. But Margaret Burbidge went on until last year. And so their vision is shown in this rather complicated diagram, that the Big Bang, which, as I mentioned a bit later, produced hydrogen and helium. And that goes into the first generation of stars. And the high mass stars live short lives, they blow their stuff back, and then you get a processing of material through successive generations of stars. So our Milky Way is like an ecological system processing material further up the periodic table, etc. Now, I am going to get out of the galaxy. If you were to get 3 million light years away from the Milky Way and look back at it, you see something like this. This, of course, is Andromeda, a huge disk viewed obliquely with about 200 billion stars orbiting around some central hub, within which there lurks at the center a big black hole. And this is very like our galaxy. This is probably twice as big as our galaxy. And it's our nearest major neighbor in space. And of course, in the large scale cosmos, galaxies are the basic building blocks. Here's another one, Whirlpool Nebula. And this is a map which shows within a certain range of latitudes, all the galaxies within about 600 million light years. Each dot is a galaxy, sort of probably a few thousand here. And the main point this shows is that they're spread through space, but they're not uniformly distributed. They're grouped together in clusters, etc. Our local group, which is us, Andromeda, and about 30 smaller members, is one, but the Virgo cluster is a much bigger one, about 40 million light years away. So galaxies are distributed like this. And of course, we can now look much further. Oh yes, let me go back and say how we come to understand galaxies. You might think it's very, very hard to understand anything about galaxies because we're pretty helpless as astronomers. If you're a particle physicist, you want to understand atoms or subatomic particles, you can get them in a lab, you can crash them together in an accelerator and see what happens. But of course, we can't do experiments on cosmic objects. And of course, galaxies change so slowly that we just get a snapshot of each one. But here, computer simulations have helped hugely, because in the virtual world of a computer, we can ask the question, what would happen if two galaxies crash together? And this movie shows an example of this. And this is a calculation where you put in gravity and gas dynamics, and you ask what happens. And when the galaxies fall together, they merge, and you would end up with no disk galaxy, but a sort of amorphous elliptical galaxy. And I should warn you that this is going to happen in about 4 billion years, when Andromeda is going to fall and mesh in with our Milky Way. And we can do these calculations, and we can do them making different assumptions about the amount of stars and gas and dark matter and all that, and see which fits the data better. And this is the way in which we have come to understand with reasonable confidence what's happening. This, incidentally, this is a real picture which shows two galaxies, and one of them has pulled out a tidal plume on the other. And having done lots of simulations like the ones I showed in the last slide, we can be fairly confident that if we came back in 100 million years, we'd find these two galaxies had merged, rather like happened in the virtual universe I showed you on the previous slide. The other advantage we have over, say, geologists is that we can check our theories about how galaxies form and evolve, because we can look very deep in space. So this is a Hubble Deep Field, which shows an area just a few arc minutes across. It would take dozens of fields like this to cover the area of the full moon. But in this small patch of sky, a very deep survey shows many hundreds of smudges, many of them galaxies fully like our own, but their lights were sent out more than 10 billion years ago, before the Earth formed. So by looking at data like this, we can test our theories, not just by seeing if we can match galaxies as they are today, but we can match them as they were 1 billion, 2 billion, 3 billion, 4 billion years ago. So we have the advantage of fossil hunters, that we can actually see the past in the way they can't. And that's how we have learned quite a lot about how galaxies evolve, which I don't have time to go into now. This is a very distant object. You can't really see it very well here, but this is one of the most distant objects for which we have a good spectrum. And this is a tracing of the optical spectrum of that object. And don't worry about the details, but the thing I want to point out is that the strongest emission line on the left of this, just above 1 micron, is the strongest line in the spectrum of atomic hydrogen, Lyman alpha, which is actually emitted in the far ultraviolet, 1216 angstroms. And this object is so far away that the wavelength has been stretched by a factor 8.1 between emission and reception. This is due to the expanding of the universe. And so we can look very, very far back to when the universe was compressed by that factor compared to now. Incidentally, this object is not an ordinary galaxy, it's a quasar. And quasars are objects where there's a black hole in the center, which is being fueled by gas swirling into it, rather like in this picture here. The gas gets very hot, and the emission from that gas and its surroundings outshines all the stars in the galaxy. So in a quasar, the gas in the galaxy is being irradiated and ionized, not just by the starlight, but by the 100 times brighter emission from the quasar. And that's why you can't get a decent spectrum of an average galaxy as far away as the one I showed you, but because it's a quasar, you can. But and this is a picture you may have seen on newspapers, which is a radio interferometry picture, which shows actually a black hole itself around a big galaxy. Well, what about the early history of the universe before there were galaxies? Indeed, was there a beginning? This picture was taken in the 1950s, and it shows on the left a rather young version of Fred Hoyle, who believed then in a steady state theory, the idea that the universe had existed from everlasting to everlasting. It was expanding, but new galaxies were forming in the gaps, etc. And on the right, there was Georges Lemaitre, who was a Belgian priest, And he, back in the 1920s, had the first idea of a Big Bang universe. And when these people met in the 1950s, we had no way of deciding between those two theories because we had no evidence far back of knowing whether the universe looked the same as were predicted or whether it was different in the past. And the clinching evidence, which showed that there was a Big Bang, even more clinching than looking at distant galaxies, came from these two people in 1965, which is Penzias and Wilson, who were two engineers working at the Bell Telephone Labs, and they had built this antenna ready to monitor artificial satellites, but they found there was excess background in their equipment, which seemed to come from all directions, and that they inferred that intergalactic space was being warmed to about 3 degrees above absolute zero by some background microwave radiation. Later work showed that that background radiation had a fairly exact black body spectrum, where the intensity and function of frequency is shown here. And that's important because this is the kind of spectrum you would get if you looked at the radiation in the center of the sun, where it's come into equilibrium with its surroundings. And so the interpretation was that this radiation was a relic of when the entire universe was squeezed hot and dense, like the inside of a star. And as the universe expanded and cooled, this radiation had its wave-varying stretched, it moved to lower temperatures, it got diluted, and it fills the universe, it's got nowhere else to go, and it comes to us in all directions now. And from evidence like this, then we have a sort of time chart of the universe, and I'll just highlight 3 things. The present is at the top, and we can look back 90% of cosmic history when we look at the most distant galaxies. When we look at the background radiation, we are looking back 99.98% of the time to the Big Bang, when the universe is 300,000 years old, because before that time, the universe was opaque, like inside a star, and the radiation we see in the microwave background has come uninterruptedly from that time. And if we go back to when the universe was a few seconds old, it would then be at a temperature high enough for fusion of hydrogen and helium to happen. And one of the bits of evidence of taking this seriously is that the universe contains hydrogen and helium in just the proportions you would calculate if you work out what would happen during the first few minutes of the expansion. Now, the microwave background radiation can be observed, and this is a projection of the whole sky, and the temperature is not quite the same everywhere. It's a bit hotter in some places than others. This is just a color coding, but the temperature varies by about 1 part in 100,000. And this is very important because if it was completely smooth, then the universe would now be just cold hydrogen, helium, and no stars, no galaxies, no people. But what happens is that the slightly overdense regions are decelerated more by gravity during the expansion, and they eventually condense out. And this is another computer simulation where the expansion is condensed out, and it shows dark matter and gas. And this shows how, as the universe expands, overdense regions condense out to make galaxies. And lots of calculations have been done of this kind. Well, we can extrapolate back with some confidence, I said back to a few seconds when helium was made, and probably back to about a nanosecond, because that's the time when every particle was moving around with thermal energy about as high as we can produce in the big accelerator, the LHC at CERN. But if we want to understand some deep features of the universe, that's not enough. A few things we'd like to know. What caused those fluctuations? Why does the universe expand the way it does? And why does it contain the observed mix of atoms, radiation, and dark matter? we just don't know that. To answer that question, we've got to go back to a very, very early stage in the universe when the physics is more uncertain. I should say that at a nanosecond, the observable universe would have been about the size of our solar system. But to understand these things, we've got to go back to when the observable universe was squeezed down to the size of a tennis ball, a huge bigger extrapolation where I put up this hazard sign because the physics is very uncertain. But there is a theory called inflation, which says that when the universe was of microscopic size, it expanded very, very fast. And during that time, it homogenized except for these fluctuations, which are quantum fluctuations, and they are the seeds for galaxies. So the fluctuations that led to galaxies may have originated as microscopic quantum fluctuations when the universe was a trillionth of a trillionth of a second old. Now, that's a speculation because we don't have any validation for the physics which applied back then. But let's hope this will be sorted out sometime. Now, do I have about 5 more minutes? Okay. Yep. If I could just have 5 more minutes, let me just say a little bit more.
So go ahead, Martin.
Okay, fine. Yes. Well, just to turn from the beginning of the universe to the far future. We've known that there are 3 scenarios for the future of the universe. They're plotted here, where time is upwards. On the left-hand side is a universe which is expanding now, but eventually the gravity between galaxies and each other will cause the expansion to stop, collapse back to a big crunch. The middle picture is where there's a deceleration due to the gravity, which everything does and everything else, but not enough to ever stop the expansion. But to our surprise, we learned 20 years ago that our actual universe, which was thought until then to be rather like the middle picture, is in fact accelerating now. And this means that there is something in the universe which exerts a force even in empty space and which overwhelms gravity on a cosmic scale, the accelerating universe. So for the last half of its life, the universe has been expanding and accelerating. And the far future, even though long-range forecasts are never very reliable, the far future is that the universe will expand more and galaxies will eventually disappear over a horizon, like what happens when things fall into a black hole. But eventually the universe will become very dead and only our galaxy Andromeda will remain in view and their stars will gradually fade out, etc. So that's the simplest long-term view. But I want to now ask another question. How big is the universe? How big is physical reality? Now, we could talk about the observable universe. I've shown you that we can see a very long way away. And there's actually a limit to how much we can see, even in principle, because as I mentioned, galaxies are expanding away and there's a sort of horizon beyond which we can't see galaxies, just like when something falls into a black hole, we can't see it. So there's a finite amount of space volume we can see. But just as if you're in the middle of the ocean, you know there's a horizon around you, but that's got no physical significance. You don't think that the ocean necessarily ends just beyond that. Likewise, in the universe, there is no reason to think that there aren't galaxies far beyond our horizon. And indeed, there are some arguments for saying that almost certainly there are. Probably the universe goes at least 100 times more. It could go on so far that every combinatorial option is fulfilled, and we all have avatars a long way away who we can be hopeful will make the right decision when we make the wrong ones, etc. So that's a possibility, but most conservative astronomers would accept that the universe goes on probably 100 times more than we can see. But that's not all. All this is what I call the aftermath of our Big Bang. And the other question is our Big Bang the only one? And there are some theories which suggest it isn't. And this is a cartoon picture, no more. Bottom right, this shows a picture of our universe, the part we can see, and beyond that, galaxies that exist but we can't see. But that whole structure could be just one sort of bubble in a sort of infinite archipelago of many, many big bangs. And this is an idea due to Andrei Linde, a Russian astronomer 30 years ago or so. And it's one of many ideas which suggests that if we understood the physics of the extreme conditions when inflation occurred, that physics may indeed predict that these big bangs keep going, many of them. So we are in a sort of ensemble of universes, not just one. And this gives an even grander concept of physical reality. One challenge is to see if we can see which part of this decision tree is correct. How many big bangs? Is it just one, or are there many big bangs? If there are many, there's another interesting question. Would they all be replicas of ours? Or could it be, as some theories suggest, that different big bangs could cool down, governed by different physical laws? They might end up with different atomic physics, a different strength of gravity, etc. And then you can ask the question, is there some sort of observed for selection? If we are in a universe that's allowed complexity to evolve, but there may be other universes where there's, say, no chemistry, or where gravity was so strong that things as big as us would get crushed, etc. This is an interesting topic, and I could spend a whole lecture doing that, but I've got no time for that at all. But let me now just finish off by returning to the more observational parts of the universe, and just make a point that the excitement which we've had over the last few decades is not going to diminish, it's going to accelerate. And here are just examples of major observatories. ALMA, which exists, this is in the Arizona desert, a sub-millimeter huge array, which is a world project. It's Europe, Japan, and United States. And I showed the ELT, James Webb Telescope, to be a big X-ray telescope, and the square kilometer array, a huge worldwide radio array with lots of antennae in South Africa and in Australia. This will be online within a decade or so. So there's tremendous excitement, and we can expect progress on the very distant parts of the universe, also on planets around stars, and also, of course, on understanding our solar system through not only these observations, but through space probes being sent to these bodies. So let me say that there's lots of speculations now, but they won't always remain speculation. And just to give an anecdote, I was at a conference a few years ago when we were talking about the idea of a multiverse, like I showed in that last cartoon. And the chairman asked, how much would you bet on the multiverse? On a level, would you bet your goldfish, your dog, or your life? And I said, well, we don't know the answer, but I would be nearly at a dog level. And Andrei Linde, who was on this panel, said he'd spent 25 years inventing this idea of the multiverse. You'd almost bet his life. And then the other person who was involved in this was the famous theoretical physicist, Steven Weinberg. He said he'd happily bet Martin Rees's dog and Andrei Linde's life on the idea of the multiverse. So it's a serious idea. It's not metaphysics, but it may well be true. We don't know for some time if it is. But finally, let me show this picture. This shows Edwin Hubble, heavy smoker here, as you can see. And he said in his classic book, The Realm of the Nebulae, only when empirical resources are exhausted should we indulge in the dreamy realm of speculation. I've done a bit of that, but I want to emphasize that astronomy has developed because of the observations and instrumentalists. Armchair theory by itself wouldn't have got us very far. So it's the instrumentalists and the observers, and indeed the computer scientists allowing us to make models who've made all the difference. So let me stop there. Thank you very much for listening.
That is absolutely marvelous, Martin. Thank you. I mean, as a as a single presentation roundup of giving people an idea of what astronomy is all about, taking us from looking around our own solar system to other stars and potential exoplanets, and then back to the very beginning of the universe. It's been absolutely fascinating. Thank you very much indeed. And now we do have a number of questions for you. So we go right back to the very first, which is, are there any plans to revisit Pluto, as it turned out to be much more interesting than anticipated?
Yes. Well, I mean, I don't know. I mean, I think probably George Tahu would be able to answer that better. But certainly it has proved much more interesting. And of course, there are objects further out. New Horizons did go to one of the major objects in the asteroid belt after going to Pluto. And I think everyone realizes it's very important to explore that. And of course, you've probably heard about the question of Planet 9, which may exist out there. But I think George will be better able to answer that question this afternoon.
Okay. I have a personal connection with New Horizons because as a mission supporter, my name was on the spacecraft. So I used to have a sign in the back window of my car which said, my other vehicle has gone to Pluto.
Very good.
And the next one, what do you think to human modification to enhance and accelerate our planetary exploration and habitation?
Well, I mean, I think I did allude to this a bit in Mars, because it's fairly clear, I think, that by the end of the century, we will have a knowledge of genetics, so we can see what combination of genes corresponds to particular desirable human qualities, and also we'd be able to synthesize a genome with those properties. So human enhancement will be possible, but I think there are ethical concerns. I hope it can be regulated on Earth. But I think if there are these adventurers on Mars, we should cheer them on in making use of all these techniques, because they are badly adapted to where they are. They need to change, and I hope that they will, and they will be adapting to Mars. And perhaps if they become cyborgs and electronic, they may prefer zero G, and they may not need an atmosphere, so they can go off into the blue yonder. So I think that's certainly a possibility. But I do think it's important that not only are human beings less useful now that robots are getting better sensors and more intelligent, but I think we ought to just realize that humans are adapted to the Earth and not to elsewhere. But a near immortal cyborg will, of course, think very differently. And just one other thing, but one other point which astronomers bring to this is to realize that the future is longer than the past. It's taken 4.5 billion years for Darwinian evolution, but the sun has got 6 billion years ahead. And so the amount of evolution in future will be more than from a bug to humans. Certainly more, because it'll happen on the timescale of technological evolution, which is much, much faster than Darwinian selection. So we just can't conceive what could happen in the far future.
Yes.
We're not the culmination.
No. It's been said that although robotic exploration of Mars, and certainly going to places where at the moment humans are unable to go, has advanced our knowledge considerably. But it's also been said that none of those robots have come back to Earth and enthralled an audience with the tales of their exploration. And then there's of course the quote from Wernher von Braun, who said that the human brain is the best computer we can send into space. It can react to the unexpected, it can learn from its experience during the mission, and of course, he added, and they can be manufactured using unskilled labor.
Right, yes. Yeah.
Right, our next question asks, if we find any form of life on Mars, however low, would we still have the moral right to take the planet as if it belongs to humans and live there?
Well, I mean, I think we'd have to preserve it. We'd have to treat it like a nature reserve with great care, obviously. And ditto if you found life elsewhere. But let me mention why it would be very, very important to find evidence for life in our solar system, particularly on Enceladus or Europa, because I mentioned we don't know whether life was a rare fluke or not. But if we could show that life had originated twice independently within one planetary system, then that would immediately tell us it exists in 1 billion places in the galaxy. It couldn't be rare and special. Now, there's one proviso in that, which is that for Mars, there's some ambiguity, because many people say that some spores or things could go from Mars to the Earth or vice versa. So you'd have to be sure that if you find life on Mars, it has an independent origin, not the same DNA as Earth. But if you found something around Jupiter or Saturn, then that would certainly have to be a separate origin. And that would really have this momentous conclusion that the galaxy would have to be teeming with life.
Okay, thank you. In the event we discover an Earth-like planet that makes all of the criteria and possibly supports life, is there a plan in place for how we would proceed, e.g. a next phase, and how would we be able to communicate?
Well, of course, there's a big difference between a planet with life on it and a planet with intelligent life on it. And of course, you know, I support SETI searches, although I don't hold my breath for success. My take on this, incidentally, is that when people talk about detecting something in space, they think of a civilization like ours, sending out signals and we picking them up. Now, I think that's not the most likely scenario, because let's think of the history of the Earth. It's taken 4 billion years for life to evolve to a technological civilization, which has existed for a few millennia at most, and is quite likely within 1 millennium that the machines will take over. I mean, despite what von Braun said, then machines will have human capabilities and certainly be far more robust and long-lived than now. And those post-humans, which are electronic, they can exist for a very, very long time, for billions of years. And so if there were another civilization, another planet, which had been following the same sort of evolutionary track as ours, then it's most unlikely that we'll be synchronized to within a few millennia, so that we would see the technological civilization. Either it'll be behind us, so we'll see no evidence, or it'll be ahead of us, so we will see evidence of artifacts. So I think the Drake equation is very misleading, because that talks about the lifetime of a civilization like ours. And even if that is only a few hundred years, then the legacy of that civilization could be machines going through space, as I've indicated might have for Mars, and they may be beeping away or malfunctioning, etc., but they will be there for billions of years. So it's far, far more likely that the evidence of technological artifacts will be through detecting something electronic like that than through detecting a civilization. So I don't hold out much hope of having a sort of a conversation with aliens who are like us in the civilization. It'll be some sort of a electronic brain of some kind. Okay,
Martin Rees, thank you very much indeed. We do have about another dozen questions for you, but we have to carry on with our program. Okay, yes. I hope if we're able to stay around with us till the end roundup session.
Yes.
Though I do know you have another presentation to give in California, but virtually.
I do, in fact, yes.
Having to fly out
later
there.
Today, yes. Yes.
Thank you again very much indeed for agreeing to speak to us today.
Well, thank you for the invitation, and all the best for the rest of the session. And I'm sorry I won't be here to hear George.
Okay, thank you.
Thank you very much. Thank you.
Right. So our next speaker then is someone who will be familiar to many of you, although you may not recognize him without his so-called spacesuit. Greg Smye-Rumsby is an astronomical designer. So unfortunately, he doesn't design galaxies and so forth, but he does artwork in astronomical magazines, and you'll know, having seen his stuff, that he is extremely good at it. His topic today, though, is, well, I was going to say it's nothing to do with that, although it may well include some of his diagrams. He's going to talk to us about solar eclipses in advance of the UK's next solar eclipse, which takes place on the 10th of June. So over to you, Greg.
All right, thank you very much indeed, Jerry. I hope everybody can hear me. Have I got control of the screen now?
You should have.
Okay, let me get my presentation. Just to warn everybody that Keynote has issues with known issues. In fact, there's a nice little warning there. Known issues with Zoom. So if it jams, just bear with me, and we'll do the very best we can. Okay, this is all about eclipses. Can somebody just affirm that you can see that screen? Jerry, can you just
Yes,
see?
I can see it, Greg, yes.
Brilliant. Now, if it jams, can you open your audio channel and just yell at me that it's jammed, and we'll just wing it as best we can. And you just have to wait around. If it does jam, it'll only jam once. So let's hope we can carry on. So this is partly a personal experience. I just want to tell everybody that there is a solar eclipse going on right now, absolutely right now as I'm speaking. And you're probably going, what? I've not heard about that. You just have to be in the right part of space where you, the moon and the sun all line up. That's essentially it. So unfortunately, because we're stuck on the Earth, we can only ever experience eclipses from that point of view. So this whole talk will be about us stuck on the Earth, looking at the sun, and hopefully, you know, we get the moon passing between us and the sun at certain times. So why do we get eclipses? Well, I've got a lovely little diagram here. This is quite simple, really. This here is the plane of the Earth's orbit. Now, on that plane, you get the sun sitting. It's intercepted right through its middle, along with the Earth. They're sitting there. That's called the ecliptic, for those who want the astronomical term. But this tilted plane is the plane of the moon's orbit around the Earth. Now, if we can get the sun gunneling down this line here as the moon crosses the node there, or likewise on the other side of its orbit, crossing the node just here, we will get an eclipse. We will get an eclipse, definitely. Okay, so that's basically my lovely little paper diagram. And that's what this diagram that you're looking at on the screen right now is trying to explain. We do need the precise lining up. When I ask people, have they ever seen a total eclipse? Oh, hands go up. Yeah, I've seen one. Yeah. And then I say to them, did you take the safety glasses off? Oh, no, I'd hurt my eyes. Yeah, so you didn't see a total eclipse of the sun. You see, that's the trick. Now, you have to actually be in the shadow, and it's not very big, the shadow. This guy here was the second Astronomer Royal, Edmund Halley. Some of you might be aware of him for Halley's Comet, not Halley, that's Bill Haley and the Comet. Edmund Halley or Hawley, that's fine, both pronunciations, but definitely not Halley. Anyway, Edmund Halley started his career at the Royal Observatory at the age of 64 years old. Okay. The Royal Observatory today has central heating. You can imagine opening up one of those lovely slits to let the telescope stare at the sky, and it's going to be really cold in the winter. So he did that, and he had a project. At the age of 64, he was going to study the Saros. Now, the Saros is a set of conditions which will repeat themselves every 18 years, a little bit over that, but essentially every 18 years, or 223 synodic months. A synodic month is to do with the sun in the sky, i.e. where the Earth is orbiting the sun, and a sidereal month is to do where the moon is relatively placed up against the same backdrop of stars. So the synodic month gives us the 29.5 days. The sidereal month gives us the 27.3 days. We're not interested in the 27.3 days. We're interested in the synodic month. And if you get 223 of those, once you've had an eclipse, you'll get another eclipse. You really will get another eclipse. And there's a few other conditions that need to be met. You can take a screen grab of this and you can see all the other various bits and bobs about Saros.
Greg, can I just interrupt for a second? It appears that, it's all right, your slide has just advanced for me, but you left it on the title page. And I've got a lot of people saying it hasn't advanced, it's stuck, it's frozen.
Good, I'm glad you intercepted me. So if I go back, can you see that one? Why do we get eclipses?
I can see that one, yes.
Good. And have I shown you that one before?
No, that's the first time I've seen it.
Right, okay. So I was rabbiting on about eclipses and how we get eclipses, and this was the slide that you should have been seeing. Now, with a bit of luck, we've done the only jam, in which case it'll now flow smoothly. I'm keeping my fingers crossed. Thanks very much indeed, Martin. That was great. Okay, so this is the slide. Can you see Edmund Halley on the screen? Hello?
Yes, I can. Yes.
Oh, great, Edmund. So this is great. So as I say, he started his career at the age of 64. He wanted to study the Saros. I mean, that's a hell of an idea. 64 years old. I'm 68, and I wouldn't want to start a project that's that long. It's like buying very old people long playing records. You probably just don't do that. Anyway, let's move on. So this is the real scale of the Earth-Moon distance. And you can see how the moon's orbit, being not round, does vary. And sometimes the moon is a little bit further from us and sometimes a little bit closer. On average, around about 384,403 kilometers, average distance. Now, if you want to know where the sun is, you just have to go either to the left of your screen that you're looking at or to the right by a distance of about 400 screen widths. So yeah, the sun is an awful long way away, and look how tiny the moon is. No wonder its shadow thrown onto the Earth's surface is so small, and you have to be in that shadow. So stepping to one side of that shadow, you won't get a total eclipse, you might get a partial eclipse. Now, I have no idea. Lord Martin Rees was going on about the cosmos and everything else and the magic of it. There is magic in the cosmos. There is no doubt about it. It's almost like those wonderful conjurers, find the lady and all that, you know, where they do this illusion that you can spot where the coin is or whatever it is. It's a bit like that we have a moon and a sun that to us in the sky, as we see them in the sky, appear to be the same size. I mean, how is that possible? The moon formed shortly after the Earth formed, a lot of stuff blasted out into space, formed a single moon, a lot of debris. Most of the debris actually fell back on the Earth, and the Earth, being still fairly molten, was able to absorb the shock. But this moon developed, it was 13 times closer to the Earth when it formed than it is today, and it's still moving away from us by a little under 4 centimeters per year. Woo, you see. So, but in the future, we're not going to get eclipses. Think about it. Now, you can see on the right there, the size difference of the moon, depending on which part of its orbit it's in, because it's sometimes closer, sometimes further away. And you can see on the left there, the difference in the size of the sun, because the Earth's orbit is not round. We're actually closer to the sun in winter. I know that sounds weird, and we're further from the sun in the summer. But overall, the moon, generally speaking, blocks the sun. But there are a few occasions when we do get, if you look at the middle of the bottom part of the screen, what we call annular eclipses, where we can see a ring of the sun's disk poking around the complete edge of the moon's disk. We call those annular eclipses. And that's what we're going to have on the 10th of June. But luckily for us, we don't see that. We'll just see a partial. I'll talk about that, hopefully before I run out of time. Okay, so these are the different types of eclipses. All the scales are exaggerated. All the diagrams are complete, you know, a bit chintzy. They're a bit modified. But look at that text on the left, and it says, and we get the shadow at best is about 250 kilometers across. Most shadow bands that you're sitting in, and you want to be in, there's only about 100 kilometers across. And that's a total solar eclipse. If you're in the shadow looking at the sun, the moon will block out the sun completely, and we will get a total eclipse. There are annular eclipses. Look down towards the middle part of your screen. You'll see an annular eclipse where we see a complete ring of fire. That will occur on the 10th of June, but you have to go be near the polar regions of the Earth to see that, up near Svalbard and parts of northern Russia and places like that. But there are occasions when we get hybrid eclipses. Now, what is a hybrid eclipse? That's where, on very rare occasions, you get the moon blocking the sun for about 1 or 2 seconds. And weirdly, this is going to sound weird again, the shorter the eclipse, the more science we can do, because we're only blocking the disk of the sun itself, not the region just above the surface of the sun. And that way we can do an awful lot more science with that and see how prominences actually function. And then, of course, we get partial eclipses. So for us and those living anywhere in the United Kingdom, on the 10th of June, we won't see that annular eclipse. For us, it will appear like an Apple logo, where the chunk has been taken out of it, a big bite. Now, here's an interesting thing. I showed you this lovely little cardboard thing here. Now, if you're going to get a total eclipse here, by the time the moon has scudded around to the other side of its orbit, half of 29.5 days, we will get a lunar eclipse. So we nearly always have some kind of lunar eclipse, either 15 days, roughly 15 days before the solar eclipse, or 15 days after the solar eclipse. And in fact, we do have a partial eclipse. I think it's on the 28th of May. How about that? And then suddenly you go roughly 15 days into the future and you get, hey, presto, we get a total eclipse, or rather a partial eclipse of the sun. So they do line up hand in glove, one side of the orbit, then the other side of the orbit. Now, for us, this is how the moon appears. If you were to take photographs every single night on a clear night and we're able to see the moon through its entire orbit, because we have new moon when it's too close to the sun. But technically, this is how the moon would appear. It does this rocking action. Because its orbit is not round, we get to see it speed up and slow down in the sky, but it also means we catch up with different hemispheres just a little bit. We also get this nodding action because of that tilt in its orbit of 5.1 degrees. So we can see about 59% of the total side of the moon facing us. And remember, the moon does spin on its axis. If it didn't, we would see the whole surface of the moon. Try a little experiment. Hold an orange and keep it facing one way in a room all the time. Look, my fingers are keeping in the same direction, but I'm now seeing this side. Do you see? So the moon does spin. This is an interesting thing. During a total eclipse, it's always best to go to NASA's Fred Espenak. Now, Fred Espenak has been around for years, and he will show you what we call a moon's limb profile, an exaggerated version of the lumps and bumps that we find on the moon's edge. And the reason why you want to know about that is to see phenomena like Bailey's beads and also the diamond ring. Exactly how are they going to occur? Now, usually, we're not interested in the first part of the moon. I mean, experts are. People who do this all the time, they're always interested in everything. But for those amateurs who've really never seen an eclipse and would like to record it of some kind, they're going to see what we call third contact. And then you might be interested in the last bit of the moon's presence on the solar disk as we see it in the sky. And then we're going to get an idea of how the sunlight might reappear on that lovely curved edge of the moon. So here is a diagram showing you all the different contacts. Now, I hope you can see my mouse. You should be able to. I'll make it nice and big. Look, there it is there. So first contact, we're reading the diagram from left to right, but the moon itself is actually moving in each of the pairs here, moving from right to left over the sun's disk. Notice it's bigger than the sun's disk. Now, in second contact, what we have now is the moon has completely covered the solar disk. So now you take the safety glasses off and you can look straight at the sun with your own eyes. I feel a little sorry for school children. I really do. I am absolutely convinced that whenever I've experienced a total eclipse, that there will be school children out there where the teachers have told them not to take the safety glasses off for fear of being sued, I suppose. I don't know. But it's reckless, because you've only got about 2 minutes where you can safely look at where the sun is in the sky, look at the black dot as my stepdaughter did tell me once when looking at a lovely little transit of Venus across the sun. It looked as if somebody punched a hole in the sun, I think, with one of those hole punches. I think that's a great analogy. Third contact is the last bit where the moon is now just about to leave the edge of the sun, and you have to put the safety glasses back on. But for experts, third contact might reveal things like Bailey's beads or maybe the diamond ring. And finally, fourth contact. Nobody ever watches fourth contact. After the third contact, they're all going, oh, right, that was great. Let's go down the pub or whatever, you know, have a celebratory drink. You don't hang around for the next, you know, it's quite a period of time, actually. The whole thing takes quite a long while. Very first photograph of an eclipse. Here it is showing you the corona, the active superheated upper atmosphere of the sun just above the solar surface, and also the lovely prominences, bright regions around the edge, like little disorganized beads on a bracelet. When we call them prominences, just to let you know, on the surface of the sun, we call them filaments. So what are referred to as filaments or prominences are exactly the same thing. It's just that there's a bit of a contrast effect. One's sort of in silhouette and the other one is in its own right, nice and bright. The search for Vulcan, appropriately named fictitious planet, it was sensed that if we could have a look at the region where the sun is in the sky with telescopes or, you know, wide field searches, we would find this planet called Vulcan, orbiting supposedly between the orbits of Mercury, the innermost planet, and the sun. And of course, the sun being all its bright light blocked by the moon, you'd be able to find it. It doesn't exist, by the way. It really does not exist. Mercury is the closest planet to the sun, and it has had a tortuous history. You can tell from what's inside Mercury, a big iron core about the same size as the Earth's core, and a rather thin mantle and a rather buckled up crust. So we know Mercury has had a very difficult history. Testing Einstein. The Eddington experiment was an observational test of general relativity organized by the British astronomers Frank Dyson and Arthur Eddington in 1919. The observations were of the total eclipse of 29th of May 1919. There were two expeditions, one to the West African island of Principe and the other to the Brazilian town of Sobral. The aim of the expedition was to measure the gravitational deflection of starlight passing near the sun. Was it a success? It most certainly was. Tick, thank you, Mr. Einstein. Fantastic. So for me, eclipses were a game of waiting. I mean, I've been in astronomy ever since I was a toddler, to be honest with you. I've always been interested in astronomy. But I knew that there was going to be an eclipse coming to the United Kingdom. Why do I have to travel around the world? I don't need to do expensive hotels and flights. There was going to be one on August 11th, 1999, and all I had to do was wait. And all my friends were saying, you're not going to watch it in the UK, are you? And I was going, yeah, I'll watch it in the UK. It'll be raining. It'll be raining. Yeah, right. So friends of mine all gathered and we went down to, as you can see with the big red arrow on the left-hand side of your screen, a place called St. Just a walk away, basically, from the absolute cliff edge of Cornwall there. The red line is the path of totality, where the maximum shadow of the moon hits the Earth's surface. 1999, August 11th. That whole week, by the way, was brilliant sunshine. We were on bicycles, we played golf, we drove around, we went to coastal resorts, everything. Thursday morning, August 11th, the weather forecaster said, I think it might be raining. It was completely overcast. This was our view, the total eclipse in August in Cornwall. There's St. Michael's Mount. This is not my photograph, by the way. I wasn't down near St. Michael's Mount, but this gives you the idea. The horizon was visible as a sort of a pale light, but it did go extremely dark. In fact, dark enough for me not to see the hands on my watch. There's a testament to how dark it got. But I want to highlight this because what happened was, yes, this is Patrick Moore experiencing a live broadcast for Sky at Night, and he has Ian Nicholson to his right there, sitting on a seat, and they were doing a live broadcast, but of course it was cloudy, and he got rather miserable and upset. But I think what he disconnected was his experience of eclipses with that of the general public, who may never have seen an eclipse. And I want to show you this medieval depiction here, which I've sort of darkened a bit to show you what it might have been like. A farmer gets up, gets out of bed, gets his trusty dog or whatever, goes out to the field, Couple of hours after getting up, it starts to get dark again. Now, there's no newspapers, there's no media of any kind, no internet, nothing. There's no forewarning of what might happen during that day. And they get a total eclipse of the sun. How long does it last? We know that eclipses only last minutes, but they didn't. Then it must have been absolutely terrifying to experience an eclipse during the days when we didn't have this interconnectivity. So what was I going to do after this? Well, what I consider quite a good eclipse, actually, but I didn't see the eclipse itself. So I was determined to see the next one. So I trotted to Africa, knowing that there would be an eclipse in north of Harare, the capital of Zimbabwe, near a place called Churchill. I traveled out there with an expedition, actually, an eclipse expedition, and several people from Croydon Astronomical Society who were there as well, and various other people. John Mason, a fantastic chap, actually, knows an awful lot about eclipses. He was on our expedition, gave talks. It was very, very good indeed. Excellent. And I decided I would take no photographs at all during the eclipse. And that's an important point, by the way. And this is a photograph I took during totality, but it wasn't set up really to record the sun. It was set up to record the people standing on this rocky promontory. The sun looks as if it's switched on. Well, it isn't. There should be a black dot in the middle there, but this is in the days of photography. Remember film, color film and all that? But if you have a look at the photograph in close up, you can actually see the planet Venus there. I think that's quite an amazing thing, really. And that was it. That was my only photograph. So I was determined not to be distracted. I wanted to experience the eclipse. Please, please don't take photograph if it's your first eclipse. You are wasting your time. Okay. Now, my wife, Rachel, wanted to see an eclipse, so we decided that we would actually go to what the Americans had cited as the eclipse of the century. Yes, it really did pass right the way across the United States. And if you were really anywhere on that line, the weather apparently seemed to be good right the way across the United States. So everybody was quids in. We decided a long time before this to buy tickets to Denver, then drive up north towards Jacksonville and Jackson Hole. And we were going to actually see the eclipse in Casper in Wyoming. So if you want to know where Casper is, there it is there. To its right, we have the lovely Mount Rushmore, and then you've got Jackson there. And of course, you also have the lovely, Yellowstone Park. Fantastic that is, and we saw all the buffalo and everything, but we were pushing the envelope for sleep because we were jet lagged and everything else, and we only had literally 2 days, day landing, next day doing the Yellowstone, and the day after that we were down in Casper watching the eclipse. Now you might think my wife here is completely and utterly bonkers because she's using a pair of binoculars to stare at the sun. Hey, they are actually eclipse binoculars, and you can look safely at the sun. Then really of no use whatsoever for trying to see any solar phenomena, because although they do dim the sun to safe levels, the detail, they show the whole solar disk, and some of those sunspots, even the ones bigger than the Earth, cannot really ever be detected through these binoculars. You can see some very large solar spots, but they would have to be about the size of Jupiter in order to do that. But what these binoculars do give you is the ability to tell people who are near you when to take their solar glasses off to get the maximum amount of time viewing the eclipse safely. You can do various things during eclipses. You can use a little colander spoon, and what you notice are the little sort of crescent-shaped views of the sun, out of focus, of course, like a pinhole camera, I suppose. And we've got the fat fingers and the thin fingers. So you turn your hands through 90 degrees. And of course, one set of shadows will have the wide shadows because the sun is no longer round. It has an uprightness, and it's a thin crescent. So it's going to give you rather strange illumination. I want to show you this because this is quite a fascinating video. Now, I wouldn't recommend anybody taking video unless you're a fair expert, but please notice that during the onset of totality, the illumination doesn't change. The photographer hasn't adjusted the exposure, and you can see up there in about the 11 o'clock position, you can see a prominence at the edge of the sun. And if I show you the other side of the eclipse, by the way, this is the same eclipse, but processed in the hands of an expert, and I'm sure Nick Szymanek and will be able to verify this. You can actually see the new moon for real, but you do need expert manipulation to make sure you can get that light level out of there. So you can see some of the seas on the moon, although they're very faint in this image. On the other side of the eclipse, the expert can get the Bailey's beads and everything else. Just to let you know, on this American eclipse, the one in Casper, I took my iPhone and I took a tiny weeny little thing like this, which gave me a magnification of about 12. And I put a solar filter in front of it during partiality, but during totality, I took this single image of the sun during eclipse. I personally think it's brilliant, but I would think that. I'm not an astrophotographer. You can see the prominence there. You can see the extension, that Y-shaped corona, very, very obvious for the 2017 eclipse. This is that other side of the eclipse coming out, and you can see it beginning to show momentarily Bailey's beads about top of the moon. Bailey's beads, lots of them, and then suddenly goes into diamond ring. And notice the exposure is pretty much perfect during the whole of this. I love these images here. My wife, being a school teacher, decided that we could take a whole bunch of kids out to Chile, to the Atacama Desert and various other things. But I was going to be part of that trip for a week. And then I was going to leave them behind and they were going to go on and do their Atacama Desert stuff. I had to come back to the UK, but we decided to go to a place near north of Santiago and a little place called La Serena. But we came inland to a little village called Vicuña, and everybody was on the mountains around us. And we thought, we don't need to go up the mountain. We can just watch the eclipse from the campsite. So we got seats out and made ourselves comfortable. And sure enough, we saw the eclipse. It was amazing. Oh, this is the village of Vicuña. Lovely little square they had. They had fun fairs set up, lectures on big, platforms with spotlights and everything. It was quite good. A bit hacky, I suppose. On the morning of the eclipse, my wife and I wandered down very early because we wanted to see sunrise on the eclipse day. Which was lovely and clear, I have to say. And we walked into the town. There was a tiny little kiosk at about 6:10 serving coffee. And there were 3 people at the kiosk. And I could hear them, and they were Americans. And I went over to them and I just hunched my back over and I just said, Espanol? And they said, oh, no, we're American. And I said, so I'm English. My wife did not laugh anyway, but I don't think they did either. I was the only one laughing. I thought it was hilarious. Anyway, this is my wife and I relaxing just after the eclipse. One thing you do notice during partiality is look at the depth of shadows, because they're wafer thin. You don't get those deep black shadows, even though the sky is clear. And those shadows get lighter and lighter compared to the overtones that are the bits that are not in shade. I want to show you the next slide because this is often not seen, not aware. It's shadow bands. Nobody fully understands shadow bands. But as I lower the exposure on my iPhone, can you see them waving across that white painted wall? Amazing. Shadow bands. This was about 1 minute after the eclipse. So literally the moon was, you can tell how thin by the curved shadows on the wall. Now, I'm going to say, what were you thinking? Because I'm going to say it again. If you are going to see an eclipse, please don't photograph it. Go there, just take some safety glasses so you can watch the partial phases of totality. Once you get into total, take your safety glasses off, really enjoy it. You've got about anywhere from maybe 1.5 minutes to about 4 minutes. The longest eclipse is just over 7 minutes. But yeah, just enjoy it. Don't take photographs. Please don't take photographs. Just enjoy it. Now, there is an eclipse coming up. First of all, this says on the 21st of June. It's actually on the 10th of June. I apologize about that. In Edinburgh, you'll see it a little deeper. There'll be a bit more of the moon bitten into the sun. But down here in London, this is what you'll get essentially at Greenwich. It's suggesting some sunspots. The sun is remarkably bald at the moment, doesn't have much activity on it. But you never know, it should start springing back into life, because the sun has that 11-year cycle, and it's well on the way back by now, technically speaking, not showing any real signs of it, optically speaking. And there is an eclipse. Now, my wife and I did travel to Iceland, if anybody's ever, and I'm not talking about the supermarket, Iceland. We went there 3 years ago on Christmas Eve. Magic, seriously magic. I've got a photograph of me outside the hotel showing my watch, 20 past 10 in the morning, and you can still see the stars in the sky. Oh, amazing. Yeah, please go to Iceland if you've never been there, which is great. But we're right in Reykjavik in 2026. There's going to be a total eclipse of the sun. We're going to go there. We're going to go there. I might meet some of you guys there. It'll be spectacular, really spectacular. Notice how the shadow misses the UK, any part of the UK, although you do get a partial eclipse over the UK. Yeah, absolutely. And I'm going to keep that short because I know that we're running slightly late, but I don't mind absolutely taking any questions at all. And I will go back to a suitable slide somewhere across here. And I hope that worked. Can Martin or Jerry open their audio channel just to make sure everything was fantastic? Hello? Hello?
Sorry,
That's all right.
Martin. Sorry, Greg.
That's all right. That's okay. Names going all over the place here.
That was as spectacular as the event itself. So thank you very much indeed. Of course, we do know in the UK that any astronomical event that you intend to view from the UK is likely to result in poor weather, as Patrick often found out. But anyway, aside from that, let me nip over to the Q&A. We'll just take a couple of questions.
If there are any questions.
Do you know anything about the USA eclipse in 2024?
Not specifically, just to let you know that there are eclipses on a fairly regular basis if you are prepared to travel. And it's the traveling. Yes. But just remember, the longest eclipses nearly always occur near the equator for obvious reasons. That I know it's only minute, but those minute bits of distances do make a big difference to the time. If you're near the polar regions, you get, generally speaking, you get the shortest eclipses. Yeah, I don't specifically know anything about that particular one, but I think it's similar to the one that was in 2017.
Which was a very good one.
That was the weather over that whole track. You're talking about, 5,000 kilometers or so of the United States, where people lining that track would have seen an eclipse virtually anywhere on that track.
Yes, it's amazing. We went from one coast to the other.
Absolutely. They were very fortunate.
Yes, I had my eye on a field in Kentucky, but actually I wasn't able to go at all. But I did see the 1991 eclipse, having learned about it back in 1964. I thought, right, nothing on earth is going to prevent me from watching this, even though I've got to wait 35 years for it.
Clouds.
But
Clouds prevent you.
well, I didn't, because a couple of years before the event, when I started planning for it, I decided Cornwall was the last place I wanted to be. There were various reasons, but the main one was I simply did not trust the English weather in the middle of August. And so I was in Rumniku-Volchia, the town which was at the point of maximum eclipse in 1991, and I saw the whole thing start to finish. Now, what else happens on August the 11th, though, Greg?
On August the 11th, 1999, what else happened?
No, every year.
The yes, 11th and 12th. 11th and 12th, the Perseid meteors, absolutely.
Yes, in my video, you can actually see two meteors crossing the disk of the moon during totality.
Oh, wow.
Which is pretty amazing.
That would be spectacular. Yeah, I'd love to see those, Jerry. I really would love to see them. Yeah.
Okay, well, thank you once again, Greg. I hope that we'll have time at the end for all of the speakers to come together for more Q&A. So in the meantime, we're about to have a break. followed by our sponsors' videos. That first break will probably not be a full 10 minutes now, but we will run our promised slideshow of some incredible artwork, this time by David Harty. So see you back here in about 5 minutes. Thank you very much. So we were about to have a short presentation from each of our sponsors, but before we get to that, I would like to mention our supporters. Astroart is, as you've just seen, David Hardy's website. Frontier Development Lab are a UK organisation that has done a lot of work with NASA. Go Stargazing enables you to sign up to make remote use of a telescope for astrophotography. And Spaceflight UK, if anybody wants an interesting and entertaining presentation on space or astronomy, then go to my Facebook page. We're delighted to have as one of our sponsors the Royal Astronomical Society, the UK's almost professional astronomical organisation.
Hello, I am Lucinda Offer, Education Outreach Officer for the Royal Astronomical Society. First, I would like to extend our gratitude to the Federation of Astronomical Societies for their members and the major contribution that amateur astronomers make to science. Secondly, I would like to introduce you to the Royal Astronomical Society and some of the programs that we offer. The Royal Astronomical Society, founded in 1820, encourages and promotes the study of astronomy, solar system science, geophysics, and closely related branches of science. Our members are primarily professional astronomers and geophysicists, with a significant number of students, advanced amateur astronomers, as well as historians of astronomy and geophysics, and others with an interest in the geo and astrosciences. Some of our key programs that might interest you are our Friends membership for those with an interest in astronomy and/or geophysics and enjoy popular talks, visits, and social events with similarly minded people, such as our Friends Only lectures, invitations to social meetings and events at Burlington House, use of the Society's historical library, and a discounted subscription to our A&G magazine. You can find out more information at our website at ras.ac.uk/friends. Our Fellows membership are for professional astronomers, geophysicists, or similar, a student studying these disciplines, or simply someone with a serious interest in them. Some of the benefits include free access to our journals, free subscription to our A&G magazine, our ever popular RAS diary, use of one of the finest astronomical libraries, free attendance to our scientific meetings, and to be a part of our driving force for campaigns, such as helping us to support the Case for Space Science in the UK. And if you're a student, we also have our Early Career Network Committee, who works to build a network of peers, putting our early career fellows in touch with those in a position to support them. And there are many other benefits outlined on our website. For more information about both memberships, please go to ras.ac.uk/memberships.
Hello and welcome to BBC Sky Night magazine. We're proud to be one of the sponsors of this year's FAS online convention. As we slowly move back to normality and begin to ease the restrictions that have become a feature of all our daily lives, the Sky Night magazine offices are reopening, and that's where I'm speaking to you from today. However, over the past 12 months, we've been mainly working from our houses. Operating remotely on Teams and Zoom, the magazine team has continued to serve the astronomical community, putting together each monthly issue of the magazine with passion, while we've all been based at home. And what a year 2020 has been. We had a bright comet, one of the best apparitions of Mars in many years, And to top it all off, the great conjunction of Jupiter and Saturn, together as the Christmas star in the lead up to the festive day. Boosted by these events, we saw a big jump in the number of new subscribers to the magazine, keen to try out stargazing. People had extra time on their hands, perhaps they got round to taking up a hobby they'd not had time to do before now. And perhaps also because the night sky is a powerful reminder that despite all that's happened with COVID, there are some things that carry on. The constant, regular, reassuring change of the night sky is one of the most awe-inspiring examples of this. A subscription to Sky at Night magazine is one of the best ways of furthering your passion for astronomy. On receiving their issues through the post each month, subscribers get updates on the latest news, expert product reviews, and engaging features on cosmology, key moments from the history of astronomy, spaceflight, and space science. Guides to astrophotography too, both in terms of capture and processing. As for practical astronomy, regular seasonal stargazing tours are an addition to our 16-page pull-out sky guide, which each month covers the best targets to track down with the naked eye, binoculars or telescopes. For the rest of 2021 and beyond, we're looking ahead to the key anniversaries and mission launches. NASA's return to the moon planned for later this year with the Artemis 1 mission, ESA's Bepi-Colombo mission getting closer to its target, Mercury, and the long-awaited launch of the James Webb Space Telescope. Plus the observing events that mustn't be missed in the night sky. This June's partial solar eclipse, Jupiter and Saturn making their best presentations of the year this summer, conjunctions of well-placed deep sky targets, and of course meteor showers. And as we move into the start of the dark sky season later this year, we'll be uncovering the little-known treasures of the autumn sky and the majesty of the Milky Way. There's much more too besides the magazine. Our bonus content section includes a virtual planetarium video guide to the night sky's best observing each month, narrated by the Sky at Night's Pete Lawrence and the University of Leicester's Paul Label. Our regular podcasts feature interviews with the brightest minds in space science and planetary exploration, and Star Diary episodes with all the top observing to be had from your back gardens. Our online lectures have gone from strength to strength, giving you access to fascinating and expert insight from across astronomy. They've included cosmologist Katie Mack, director of the Vatican Observatory Brother Guy Consolmagno, and comedian and Stargazing Live presenter Dara O'Brien. We have some really exciting speakers to come for the rest of 2021, including a look at Yuri Gagarin's historic first flight to space 60 years ago this month. To help you take advantage of all that we've got coming up, we've put together an exclusive subscription offer for this convention. Try 3 print issues for just £5 when you sign up by direct debit. Visit the link shown here to take up the offer, and I wish you happy reading and clear skies.
Hi everybody. Thank you to Jerry Stone and the committee for the opportunity to be here with you today. Under different circumstances, of course, as in previous years, the Widescreen Centre would have a stand and some telescopes outside the meeting hall, and we will be catching up with you all individually throughout the day. The Widescreen Centre is 50 years old this year, the company starting out in a back room in Marylebone High Street, assembling anamorphic lenses, hence the name Widescreen Centre, before relocating to Dorset Street and diversifying. Still in Sherlock Holmes territory, where the company remained until Elena and I moved it to Cambridgeshire in 2016, which amazingly is almost 5 years ago now. 1971 also marked my beginnings as an amateur astronomer, so I have my own 50th anniversary this year. During my first trip to the US, Mars was at a very close opposition, as some of you may recall, and Apollo 15 was on the moon. That was it. I was hooked. It's great to see so many kids of all ages go through the same process today, and we as a telescope retailer are here to help with good, impartial advice and a very wide range of brands and models. In recent times, while people have been at home, many have turned to the night sky, and it's great to see so many new people in the hobby. From our interactions with them, we think very many of them will remain as amateur astronomers. We sell a lot of beginners telescopes, and we always try to offer people a choice and explain our recommendations to them. We will never sell people anything which is wrong for them. With the sun now gaining altitude in the sky and getting more active again, as always, we carry and store a wide range of solar astronomy equipment, telescopes and accessories, white light and hydrogen alpha, from Daystar, Lunt Solar Systems, Barda Planetarium, Kendrick, and more. With the partial solar eclipse now less than 8 weeks away, now is the time to make sure you have everything you need for June the 10th. The Widescreen Centre has a new brand to introduce to the UK market. Some of you may have noticed the 2 refractors here in our showroom. These are the first offerings from Founder Optics, designed in Japan, built in Taiwan. We have here an 86mm and a 106mm, both Apo triplets, both with 2 elements of ED glass, both with widely spaced lenses. Both come supplied in an aluminium case with an optical test certificate and with a field flattener available for each of them. As wide-spaced triplets, they are a design often associated with Takahashi and their TOA range. As such, with the specifications they are slightly larger and slightly faster than other commonly encountered scopes from Taiwanese manufacturers. These will provide an exceptional viewing experience and will excel for imaging. The larger of the 2, the 106mm, comes in at just under £2,000. Interest in astro imaging also continues to increase, and we supply mounts from amongst other Skywatcher, Celestron, Avalon, 10 micron and more. Whatever telescope and camera you're using, from travel mounts including the Star Adventurer through intermediate go-to mounts up to full observatory spec equipment, talk to us for advice. As always, here at the Widescreen Centre we hold good stocks of all the leading brands, from Teleview, APM, Takahashi, William Optics, Explore Scientific, ZWO, Prima Luce Lab, Astronomical, and some relative newcomers to our range, Optolong, IDAS, Pegasus Astro, and we hold good stocks of everything wherever possible. We supply equipment at all levels, from a quick solar filter for the eclipse or a deep sky filter for galaxy season to a complete new telescope, or for a full installation. We're here to help and will impartially guide you or your society's members through the range of products available in 2021. We're looking forward to reopening our showroom and getting back on the circuit and seeing everybody face to face at the exhibitions and events once more. In the meantime, enjoy the remainder of today's talks and email or call the Widescreen Centre for your astronomy needs. This is Simon Bennett from the Widescreen Centre in Sutton near Ely, Cambridgeshire. Clear skies everybody, keep safe, and we will see you soon.
We're going to move directly on to our next speaker. Nick Szymanek will be well known to many of you, particularly if you've tried astrophotography for yourself. And he has become one of the UK's greatest exponents of this field of astronomy. From whether you want to take just a simple picture, perhaps of the moon or so forth, then you can get guidance on this subject through Nick's various books, his ongoing articles in the Astronomical magazines. But now he's going to tell you something about this live. So Nick, over to you. Thank you.
Hi, Jerry. Thanks for that. Okay, is it okay if I share my screen now? Jerry, can you confirm that you can see that okay?
I can confirm that, Nick. I can
Okay,
see.
thanks, Paul. Okay, well, as you can see from the first slide, we're talking about photographing the night sky, and it's a pursuit that has become incredibly popular over the last 10 or 20 years. And I've got a lot of stuff to get through here today for you, so I'm going to go through this fairly quickly. And it is, of course, somewhat of a personal view. It's just easier to use a lot of my own pictures for this to get around any sort of copyright issues. But we can go straight in with, let's just make sure we're still working. I can show you sort of rather embarrassingly two of my very own first astrophotographs. The one on the right, of course, is the moon from memory. This would be about 1983, taken with just a zoom lens and then printed onto photographic paper at sort of quite a large magnification. On the left, which is just a scan of star trails and a tiny little fuzzy blob. I hope you can see my mouse cursor. This is the comet Iras-Araki-Alcock, which I think was in 1983, a very close passing comet to the Earth. So I was able to just get a kind of fuzzy streak there. But of course, astrophotography takes all sorts of forms from all levels of complexity. As we go through the talk to the end, if you remember back to that first picture and something like this, you'll be amazed, I think, about how much the hobby has evolved over the years. And of course, an astrophotograph is just something with vague astronomical interest in it. These are film shots, by the way. These are dating back to the early 90s. This one here, I think, is about 2000, when we had a very nice auroral display over the southern UK even. And this was a picture I'd taken from my back garden on film. And of course, everything was an experiment back then. We couldn't see an instant display of what we just photographed. So it was a bit of an experiment, but happily these came out okay. And these were just kind of guessed exposures on a static tripod, and they actually came out quite well. And of course, in April 1997, we had a remarkable viewing of the wonderful comet Hale-Bopp, and that is a good representation of how it looked. It's not the best comet photo I've ever taken, for sure, but it gives a very good representation of how the comet looked in the sky. And then, of course, attaching the film camera to a small refractor, it gave this enormous jump in resolution. We could see right in now to the ion tail, the blue ion tail and the dust tail. And although this was a film shot, the original slide was bright green, just completely wiped out by sodium light pollution. But of course, around about this time, we did get access to film scanners, which allowed us to digitize these images and then sort of manipulate them in terms of a processing sense, like we do today. The sun, as we've heard, it's a very interesting target. Back in the day, and again, I think this is the early 90s, we didn't really have access to the really good images that we can take today using hydrogen alpha equipment, but it doesn't matter. We could use this relatively cheap equipment to safely photograph the sun on film, and this shows a nice group of sunspots. The sun was particularly active at that time. Now, constellation photography back then was also remarkably difficult because the camera and lens combination see a wide field of view. We see a big area in the sky. And of course, light pollution will always get into there somewhere. So we get these horrible gradients, which, we still do today, of course. And really, it's, back then there weren't the really good choice of filters that we have today for sort of blocking light pollution, particularly with DSLR cameras. So I traveled abroad to darker skies, and you can use exactly the same equipment and film and everything, in this case Elite Chrome 200, to take much longer exposures than the previous shot, which was so badly affected by light pollution, and to see much fainter targets in the sky. Hopefully you can see things like Barnard's Loop on here, and I think the Horsehead Nebula is in there somewhere. It's a very rich area of sky. Of course, this was from the Canary Islands, and even going out there to do astrophotography, I always enjoyed just setting up a camera on a tripod and photographing star trails, for example. If you have a fairly exotic foreground like this, it makes a huge difference. This one gives you an idea that if you're photographing north, so up, you may recognize most of the stars of the Plough asterism down here. The other two are hidden behind the dome, but you can extrapolate the line for them up to Polaris, and you can see that the actual center of rotation is much less compared to a little bit further away. And of course, this was also illuminated by moonlight. It's something like about a 10-minute exposure. So the moonlight's gone a long way to illuminating the white domes, of course, and the car on the left and the sea and, the clouds and stuff. Gives you this sort of evocative view of the sky. When it's completely dark, you can extend those exposure times. And again, pointing straight up to Polaris, you get these lovely sort of concentric star trails of varying sizes. And you can also see here these bands of air glow in the atmosphere, just natural atmospheric emission. Again, this is probably a longer exposure, this one, probably about 20 minutes or so. And also this one here actually taken from Hawaii up at 14,000 feet with the center of rotation on the left, just out of the field, much lower in the sky at 19 degrees north of the equator. The Polaris is actually pretty low in the sky. And just during the course of this exposure, you can see we captured a nice bright fireball at the top left. Milky Way photography, again, from dark sky sites was quite rewarding on film. The film had a natural warmth to it. You know, it doesn't have the sharpness of modern DSLR cameras, but it had a natural warmth to it, which was very nice. And again, we could scan these and just do a little bit of perhaps sharpening or perhaps just boost the contrast a tad. To capture some very nice views of the summer Milky Way, particularly around the area of the teapot of Sagittarius, which you can see here. So you've got things like the Lagoon Nebula and the Trifid here, which leads me on to the next slide, because still with film, again, with the lens removed, in this case, a 50mm lens and a short focal length telescope, a 500mm Pentax refractor, you can zoom right in on this area here and capture much more sort of detail. And now, you know, this is starting to resemble more the astronomical photographs that we're used to seeing everywhere today. So the E200 film was a very good candidate for a deep sky astrophotography. And of course, everything changed with the advent of these. I mean, these have been around a while now, modern DSLRs. The original ones, I think, probably came out perhaps late 90s, early 2000s. And, you know, they were kind of groundbreaking, but because the consumer market has been so interested in these, that they've just kind of completely taken off, and they're fantastic tools in the arsenal of the modern astrophotographer. You know, I don't use them that much myself, but you know, a lot of people, when they're starting out, it's one of the three things they need for astrophotography. It's a camera that they need. So modern DSLRs, they're cheap. You know, they've got good features like the live preview, they're sensitive, the noise levels are coming down. So they are fantastic tools in the hands of seasoned and beginning astrophotographers. Classic targets, of course, are things like noctilucent clouds. And again, in the old days of film, this might have been a little bit hit and miss, but with a modern DSLR, I can take images like this in just a few seconds. You see the results instantaneously. In this case, I've actually auto-focused on the trees in the distance. Well, this was about 4 o'clock in the morning. The camera could differentiate between the sky and the ground. It actually just auto-focused. So in that way, you tend to get the sharpest images. And also another great love of mine is meteorological photography. So even for the daytime stuff, like you see here, this sort of artificial or earth rainbow, I call these, an artificial rainbow captured in a field irrigation spray. You know, they're great for seeing how your results are coming out. And of course, you get them under a dark sky, like in the Canaries, and you can see this multitude of stars in just these short, relatively short exposures. So, you know, it's a fantastic piece of equipment for the modern astrophotographer. But of course, for the best results, it does need to be coupled with some kind of tracking drive. And, you know, back in the day, people attempted to make the Scotch mount or the barn door mounts, these sort of things, with sort of limited success. But thankfully, you know, in the sort of mid-2000s, we started to see a kind of influx onto the market of these so-called star trackers. And one of the very early ones, and one I'm still using today, as we'll see, was the AstroTrack, which I'd reviewed for Astronomy Now magazine. And I liked it so much, I just sort of bought it pretty much on the strength of my own review. And it's been out to the Canary Islands, on the left to Tenerife, where I actually carried out the review. Tenerife Observatory, on the right to La Palma, and it's great because it's portable. It's designed to be placed on top of an ordinary photo tripod. You need a ball and socket joint just to move the camera separately, and a pole finder here just to give you polar alignment. But you know, these are great if you're going abroad for a family holiday or just traveling out to a dark sky site. You know, you can take these things with you and they'll perform really well. As you see here, it's a 2-pane mosaic of the Milky Way from La Palma, again in the Canaries. And these are just 30-second exposures on the AstroTrack. So with an exposure that short, the foreground, if it's you know, a fair way away and just using a very wide lens, you get sort of minimal trailing. And again, it's perfect for doing this kind of stuff where you want minimal trailing, but the foreground moderately sharp. And of course, although that didn't have it, the newer versions all have half sidereal tracking on. So that allows you to build up these images where the sky and the foreground actually trail at half the sort of rate. And, you know, there's a good need for that. Now, I called this my little astro tracks, not out of retirement, but I hadn't used it for a while. And of course, we had a lovely apparition of Comet Neowise in the summer in the midst of the lockdown. So vastly reduced levels of light pollution and air pollution, particularly. And all of a sudden along comes this wonderful comet. And I remember my first view of it once it had really developed through the clouds, and it looks just like the sort of classic comets we remember back from the 60s and 70s. And you know, it's really exciting to be able to see this with the naked eye, but as well as with basic photography equipment. Sadly, I couldn't see it from my observatory. That part of the garden was just a little bit in the wrong place at the wrong time. So hence the previous slide, I was taking the astro track round on the tripod with the Pentax telescope, and also just using a lens as well to get a nice wide field of view. You can see at this point, in its sort of moderately brief apparition, that it had developed a nice blue ion tail, you know, not too dissimilar to Hale-Bopp. Then of course the comet developed, got brighter and brighter. We had a good run of clear nights over the summer, so I was out there every night just taking these. And this is one of the last ones I took. From this point, the comet started to fade quite dramatically, but by this point it had surrounded itself in this sort of green halo, which you know, we do see quite regularly in comets. We even got lucky and just captured an early Perseid there, I think. There are plenty of others on the market to choose from, such as the Vixen one. I've used this before. This is very good. Looks very different to the Astro Track, but you know, it works equally well. And another one which I reviewed for the magazine is this Fornax Mounts Light Track. And again, this was like a kind of a newer version of the Astro Track from a different company, of course, but this used a friction drive, but you can see it's still got that kind of long arm that sort of separates as the tracking continues. So this was a very high quality mount, without a shadow of a doubt. Now, very recently, I was lucky enough to be able to review a new generation of star trackers, and this device has its foot kind of in both camps. It's in the configuration you see it here, it is just being used as a star tracker. So you have this drive module on here. You can see the polar alignment telescope latched into place there, and then the usual sort of ball and socket joint of my Canon camera on the top. And this is a very, very high precision tracking mount that actually uses encoders for increased precision. And boy, did that pay off. But the nice thing about this, this tracker is that it can be mated with a second drive module to give this configuration here. And I hope you can sort of make sense of this. This L-shaped configuration is two of the drive modules put together at right angles. So one is for the RA drive, one is for the DEC drive. And to test this more as a kind of equatorial drive rather than just let's say a common or garden star tracker, and none of them are that, of course, but with the additional weight of the Pentax telescope and the heavy camera, you know, I needed to put counterweights on and stuff like that. So this was just a snapshot showing what it looks like. In reality, it was set up much more stringently than this. Now, this really, this drive from AstroTrack, the AstroTrack 360, this is a drive which is setting a standard beyond all of the others, I suspect. And if you're wondering why I say that, have a look at these next few pictures. Now, whilst this is not exactly the sort of prettiest astro photograph you'll have ever seen, the reason for that is it's a 20-minute exposure with the Pentax 500mm telephoto, 500mm focal length telescope with a full moon in the sky. So it's the 3 belt stars of Orion, and it is just a single unguided, it's not in terms of it's not being used with an auto guide, it's just tracking the sky on its own. And this is a single 20-minute exposure, and you can see the star images are absolutely incredible. And, you know, 20 minutes without any, you know, help from an auto guide is actually quite a remarkable achievement. So I've made it a little bit more palatable so you can see what's going on. You might be able to just make out the Flame Nebula here, just to the left of the Zeta, I think the star there. And once again, the star images, as you can, it's the same image as before, but I've just scaled it so it looks a bit more like an astrophotograph. And then for the final one in the sequence, what I've done here, which looks a little bit odd, but I've actually combined two images. I've started off with the first 1 minute exposure, which is the one with the smaller stars. And then during the course of the next hour or so, I've gradually built up those exposures until I've increased them up to 20 minutes. Now, what I've then done is I've taken the first exposure and the last exposure and blended them together just as a blended layer. So you can see the shift in the star positions during the course of an hour of auto-guided exposures. And it really is remarkable. I mean, the small drift that you see here is probably, or primarily due, I'm absolutely certain, just to probably a minor polar alignment error. But you can actually see the first exposure is within the end of the bloated 20-minute exposure at the end of the sequence. So it's it's a drive that's really a game changer in that sense. The use of the encoders on the axes of both of the axes, and auto-guided capability. And at the time it didn't have it go-to capability, but I believe that's been instigated now. So it's a real kind of leader in terms of these sort of star tracker performances. But sort of back to reality now, coming back to astro imaging with DSLRs, again, perfect for events like this, where last year we had the lovely passage of the bright planet Venus close to the Pleiades. Sort of came up here, I think, so passed very close to the Pleiades here. This is just a DSLR shot. And of course, as Greg was talking about, eclipses, in this case, a lunar eclipse. This was from January 2019, very early in the morning, but an absolutely gorgeous eclipse. And again, DSLRs are absolutely perfect for this, because you can see your results instantly. You can be sure the focus is good. You can be absolutely certain that everything is as it should be, and you can experiment with the exposures and stuff like that. So absolutely great for this sort of thing. And of course, even transits of the inner planets. Now, transits of Mercury, they're not as dramatic as of course the transit of Venus that we had, but the great thing is, I just cranked out the old filter that I used for that first sunspot shot. It's still fitted on my other telescope, which I've got now. I got rid of the original one, and again, they're absolutely great for photographing transits. You can check and refocus every so often just to make sure everything's okay. And here you can see the little disk of Mercury and a couple of little sunspot groups here, quite nice. And of course, the inevitability of doing anything like this is the onset of clouds. And just after taking these pictures, I think this was in 2016, there was a band of cloud moving up northwards, and within a few minutes of taking this, the sun was engulfed. So disappointing, but happy to get even just one shot, to be honest, but got a lot more than that, in fact. And things like the zodiacal lights, I'm not sure how clear it is on here, but it's something that in the old days I'd have photographed using 20 or 30 minute exposures. With the DSLR, do it in just a couple of minutes. You can see a preposterously low crescent moon just about to set here above the clouds. And once again, DSLRs are absolutely superb at capturing all of these sort of faint stars visible from a dark sky location. So, in that sense, not only do you get the increased sensitivity, you don't get the sort of blobby halation effects that we used to get from long exposures on film either. So DSLRs do tend to give you that nice sort of crisp view. And of course, to do the job properly, if you're imaging something like the Milky Way or a chosen nebula or a galaxy, rather than just doing a 2-minute exposure or something like that, if all your equipment's working okay, go for maybe sort of 5-minute exposures, but take 10 or 20 of them, and then you can stack them all together to produce a nice rich image. And likewise, again, if you're lucky enough to work from a dark sky site, you can move the camera across the sky. These were all taken on the Astro tracker, I recall. You can take multiple exposures across the sky and then use software to blend them all together. These are just single 5-minute exposures. But once again, if you stack a lot, you can get a much richer view of the gas and the dust that sort of that sort of invades the edge of the Milky Way, as you see there. So it's a really nice target, and it responds well to DSLRs. Now, of course, there's the other sort of camp, if you like, the sort of die-hard imagers using a variety of equipment. Now, this is pretty much the same equipment that I've used in my sort of back garden observatory for must be nearly 10 years now. It's a system that works very well. So it's mounted on one of the old original Paramounts. There's a 10-inch Ritchie Crescent telescope up here with a carbon fiber tube. There's a William Optics 73mm refractor on top, and a pair of QSI CCD cameras, all contained within the dome at the end of the garden. You can see here, that's the observatory. In fact, you can see it here looking nice and sort of cozy in there. And the idea of having a dome, of course, is that you're ready to go at a moment's notice. I can be up and running in just 2 or 3 minutes now. And even at the distance of the observatory down at the end of the garden, I can still just control all of this from indoors, just using an internet sort of screen sharing program. We use one called Splashtop, which works really well. But I mean, whilst I would recommend anybody, if they can go to the expense and it's feasible to put something like this in your garden, it just makes life so much easier. But there's more people out there, I know many of them, that tend to prefer to just take their gear out every night. It's not practical to have something like this. So in this case, I've called on my good friend Steve Hellitzer. I've borrowed some of his pictures for the talk today. We'll see some more in a minute, but for now, this is his variety of telescopes and mounts that he uses in Hertfordshire to get really good results under difficult conditions, as we'll see in a minute. But this is more typical of the sort of amateur astronomer who prefers to just take the stuff outside, set it up, and just image on a sort of nightly basis. You can see a variety of cameras here. A lot of them are very red. As a solar telescope here. We'll have a look at some images with that in just a minute. So this is more typical of the back garden imager. Now, CCD cameras have a variety, or CMOS cameras have a variety of uses, not least to actually photograph the moon. I discovered quite by accurate that if I a black and white image, if I photograph the moon using narrowband filters, you actually get a really nice, sharp, contrasty view of the moon. So every so often, whilst I sort of generally lament the visibility of the moon in the sky, I will turn the telescope onto it just to take a couple of snapshots. And of course, again, with CCDs compared to film, this is another sunspot group taken with a white light filter, but this time with a camera, CCD camera, much more sensitive. You take much shorter exposures. If you take plenty of them, you'll freeze the seeing effectively and get good ones. And if you take that to its extreme, you'll of course use a webcam to do the job. That's a different field of astrophotography altogether, which I won't touch on here. I mentioned the transit of Venus earlier on. This was it back in 2004. And once again, it's just a white light view of the actual event taken from our back garden, just using a Starlight Express CCD camera back then. And compared, for example, to the transit of Mercury that we saw earlier on, it's obviously much more dramatic compared to that. And I don't do much solar photography. I tend to leave that to the dedicated guys, but I did dabble. And this was once again with the Starlight Express camera, just using a Coronado 40mm hydrogen alpha filter. And of course, the idea of that, it does give you a chance to see much more detail on the sun. Greg talked about the prominences around the edge as well as the filaments, actually the same things, but we're seeing these in silhouette against the sun, and they look much darker when you see them here. So to show the filaments and the prominences at the same time, I've had to process the same image twice and then just blend them together to kind of expand the dynamic range of the solar image. But this is a kind of the lower end of what you can expect to get these days. People with better filters and with webcam technology are getting far better images. Now, of course, back to CCDs or CMOS cameras, monochrome CMOS cameras, the way we tend to work is to take multiple exposures through 3 filters for RGB imaging, red, green and blue, as you see here. And a classic example is the older Orion Nebula there. On the left, I've just drawn the sort of colours around the edge to show that this was taken with red, green and blue filters. The view of the Orion Nebula with the monochrome camera does look quite different through these 3 filters, as you'd expect. So the idea is that once you've taken those, you can combine them in, you know, any sort of modern program will do this now to produce an RGB image, and you can see that on the right. Now, actually, that's not all we do. We do tend to make life a little bit more difficult, but for the very good results that we get is to take a deep luminance image, which you see on the top left, with a clear filter that has the same optical characteristics as the RGB filters. And then you shoot the RGB data, and then you create what's known as an LRGB image. It's just a 2-layered image. I tend to have the luminance on the base blended with the color sort of floating above it. And you can manipulate, you can process those 2 separate layers completely individually. So it gives you quite a lot of flexibility. And then finally, we have the narrowband imaging with the Hubble palette picture. And so three types of filters, sulfur 2, hydrogen alpha and oxygen 3. We map them to specific channels in an image, and it produces the famous Hubble palette. Now, to be perfectly honest, the actual Hubble palette is just bright green with magenta stars. And this is because the hydrogen alpha component, which is placed into the green channel, overwhelms the other 2 channels. So you end up with a bright green image. So most of us, probably all of us, to be honest, do a little bit of further manipulation to convert it from that green and magenta image into something that resembles something of hopefully some sort of aesthetic beauty. And also it just demonstrates very clearly the sort of physical effects that are going on within the nebulas that we love so much. And I'll show you some much better examples of that in a minute. For now, though, classic targets, of course, have to include things like the Horsehead Nebula, a dark nebula, in this case silhouetted against the glowing hydrogen filaments behind. It's a narrowband image. Another one here, this is the Orion Nebula. This is a combination of hydrogen alpha and RGB data. The hydrogen alpha gives you the incredible detail, for example, in the trapezium area. You tailor the exposure so it doesn't overexpose the brightest stars in the image, but particularly in the trapezium here. And the narrowband filters are really good for that. And then you just overlay the color data. It's a little bit more tricky. This technique isn't easy. You can end up with things that are a little bit ugly, but you know, it does pay off to give you that ultra high resolution and the sort of 3-dimensionality. Or you have a true narrowband image in the Hubble palette. So again, you've got the greens and the blues and the golds and the yellows and reds and stuff like that. But again, good structural detail within the trapezium area and all these lovely sort of gaseous arms in the nebula. With the Pentax, it gives a nice wide field of view. So this is the sort of typical thing that amateurs you know, will take using either a CCD cam or CMOS or even a DSLR these days with a small refractor. And likewise here, large targets like the Rosette Nebula, as you see here, respond incredibly well to narrowband filters. And bear in mind that on this scale, the full moon was sort of fit in here quite nicely. So this is a large area of the sky, but you know, with narrowband filters, you get this glorious view. And also they do help to block out a lot of the sort of low. Remember, this object's fairly low in the sky from the UK, not too bad, but it's fairly low. So it does tend to block out a lot of the light pollution and things like this as well. The Andromeda Galaxy, a real sparkler, you know, another of the first sort of 3 things to go for people starting out in astrophotography. And this is a very deep image, about 26 hours in total from where I live here in Boxted in North Essex. And this is augmented with a 5th filter, a hydrogen alpha filter, to capture the lovely sort of glowing hydrogen 2 regions within the spiral arms of the galaxy. Now, there's more scientific pursuits as well for deep sky images. You know, whatever equipment you're using, this was a very nice supernova that appeared in the galaxy M61 about this time last year, I think it was. And although M61 is low in the sky, so it's in a bigger air mass, so the seeing's not sort of great, it was interesting to shoot an LRGB set of data on this and see the different color of the supernova compared to the other 2 sort of field stars nearby. And also for pure scientific research, and I was asked to contribute to an extrasolar planet transit, which Lord Rees spoke about in the first talk He showed the graphic of the planet sort of scuttling in front of the remote sun. And this was a night's worth of imaging on that. And whilst the data is sort of jumpy, this is due to seeing presumably, a good friend of mine from the BAA sort of reduced this for me. You can definitely see this dip in the sort of the graph produced by the data used with the CCD camera. And these are very, very small magnitude dips. If you look at these magnitude values over here, they're very, very small, but it definitely shows that effect. So, you know, this is a really kind of popular field for people who wish to do scientific research with their own equipment. Now, I've talked about CCDs, and I'm going to talk about CMOS cameras, because these are kind of sweeping across the field of amateur astrophotography. And this is, they're cheaper, the technology's really improved a lot over the years. And these are really sort of high performance cameras now, even to the point where they've kind of caused the demise of CCDs, which I personally find incredibly disturbing as a sort of dyed in the wool CCD right from day one. But, you know, times are changing, and, you know, these, for example, this color camera you see here, this one here, when they're coupled with the new breed of sort of high performance filters, such as the Altair one there, or the Optolong ones. These two are very popular. The L-Enhance filter at the bottom, the L-Extreme filter at the top. These allow you to take what really looks like narrow band images using a one-shot color camera. So without all the faffing about with expensive sets of filters and filter wheels and the sort of complexity of the long exposures and everything, which I actually love. But, you know, with people, again, like Steve, I'll show you some of his images now. You know, they're getting great results from a very light polluted back garden using these techniques. So again, you can compare this, our old friend, the Rosette Nebula. We saw this a few slides back, and you can see that it's produced a very good narrow band type rendition. And if I show you a picture that Steve sent me of his back garden, with the usual sort of uncaring neighbours decided to floodlight their back garden with these blue lights to match the landing strip at Heathrow, you can see not only is the light pollution in the sky, which, you know, we all contend with, but, you know, he's got severe levels of light pollution in his back garden. But again, with the modern techniques and with the will to succeed and the time to spend on the image processing, again, you know, he's producing great images. Our old friend, the Orion Nebula, this time with the Running Man Nebula to the north, and a recent picture that he took under the same conditions of M51, and NGC 5195, I think is the smaller galaxy. It's 4 or 5. This pair of interacting galaxies. So, you know, under severe light pollution, with the will to succeed, and with, you know, good equipment and good techniques, you can get some really great images like this, which would have astounded us, you know, just 10 or 15 years ago, maybe. Now, very topically, the next slide will introduce you to another thing that we have to contend with, and this was brought to my horror last night. Actually, this sequence of exposures I'm going to show you were taken last night. Now, I've laid the 6 images here. These are 10-minute exposures with the equipment I showed you earlier on, and you can see the first 5 of them had these really bright satellite trails going through them. Now, the field of view of my camera and telescope isn't that wide. You might recognize NGC 4565 here. And 5 out of the 6 shots had these really bright satellite trails through. So, you know, this problem really isn't going to go away, and it's only going to get worse. Now, there are techniques we can use which are outside the scope of this talk, but, you know, if you, for example, stack these 6 images together using this one that doesn't have a trail as a reference frame, it can help to reduce the effects of the others. And if you stack lots of images, without trails, it does not get rid of them, but it reduces them. And at the end of this session, after I'd shot the red, the blue and the green, I actually went back and shot some more red stuff to sort of replace these others. So again, it's a big problem. Now, again, this is Steve's solar setup. I showed you my sort of humble offerings, but again, with a good setup like this and with good sort of processing skills, you can take really nice images of the sun. So again, this is kind of where things are at the moment with this high quality instrumentation. You know, things are getting really good. So thanks to Steve for those. Now, software has also come along in leaps and bounds. A very popular one now is PixInsight. I use it myself. A lot of amateurs, once they've gone through the pain barrier of actually learning how to use it, and to be fair, there are a lot of tutorials on YouTube that can assist with that. It's a very powerful program. It's got some great features in that can sort of help, you know, get the best out of your data. But a relatively new kid on the block, and don't laugh, please, but Affinity Photo, it came along some years back, but has kind of got very popular now because it's a very viable program for sort of daytime photography to Photoshop. It's pretty much Photoshop's equivalent now. But rather than paying a monthly subscription for it, you can get it on sale at the moment, if it's still at the same price, for about £24 as a one-off fee. And it's updated all the time. So it's a really, really nice program. So, you know, I was tending to use it more than Photoshop because it seems to be faster and more efficient to use. But very recently, in one of the recent upgrades, we suddenly had an astrophotography stacking routine in there. Thanks to James Ritson, I think, an Affinity employee, an expert on Affinity, but also an astrophotographer himself. So I think he's managed to incorporate this in here. So it now enables you to stack 32-bit FITS files and apply basic processing to those. It allows you to build a bad pixel map, do all of the calibrations and do the stacking, and alignment, everything's really good. So for a sort of 24 quid program that's great anyway, it's now got these additional features. And I suspect with his input, we'll see more and more of these new sort of features appearing. Now, there's three other programs that are also very useful. If you compare the left and the right images here of the Eagle Nebula, this was carried out using a program called Topaz Labs Sharpen AI. And it acts a bit like a deconvolution program. So it allows you to eke a lot more resolution out of these images using this. And also Gigapixel AI, which is actually a resampling program, but because it has this sort of AI capability, it's a bit of a buzzword now, you can hopefully see the difference between the image on the right and the image on the left, particularly if you look at this area in here and the detail within this outflow. And this was just by resampling the image. So, you know, I find it useful as a resampling program, but it's also very good at actually sort of deconvolving the image even. And then the last of the three from Topaz that I use is denoise. And what we're looking at here is just a single 10-minute H-alpha exposure of the rosette, again, just the central part. And on the right is the denoised version. On the left is the original version. So you can see there's a big difference between the two. And because it is one of these so-called AI algorithms, it doesn't do too much damage to the stars. It doesn't bloat the stars in any way, but it does a very, very good job of smoothing out the background noise. So all three of these programs are well worth a look, and they all have 30-day trials free. And then for the last section, I've got lots of pretty pictures to show you here, and I hope you enjoy looking at these as much as I did, you know, putting them together and sort of taking them. Remote imaging, of course, involves two things: either setting up an observatory abroad or hiring time on telescopes in observatories abroad. By abroad, I mean in places where there's no light pollution and the sky seeing's great, much clearer, a much larger proportion of clear nights. And these are sort of typically all around the world. Well, you know, our first introduction to this, me and Ian King, was in the Astro Camp in Spain, and we had a couple of happy years just controlling our equipment remotely, particularly during the course of the summer, where we could set up exposures to run every single night and build up images like this, which are typically 60 or 70 hours worth of exposures using narrowband filters. And this is just a part of the Pelican Nebula in Cygnus. We also used a refractor for a while. This is a deep image of M33, once again augmented with further exposures through the hydrogen alpha filter to pick up these incredible glowing H2 regions. So it's a very, very deep exposure, about 50 hours worth in total. And a more recent one, we've since moved from that to another observatory, which is a very nice place to be. And this is a deep exposure of the Wizard Nebula, NGC 7380, in Cephas. And again, this is probably 60 to 70 hours worth through the three narrowband filters. And it's the Hubble palette once again. And as I alluded to earlier on, I think what I like about the Hubble palette, it does deliver these very sort of nice to look at images, but it does impart a very nice sort of three-dimensionality where you have this glowing red dust and gas apparently in front of these sort of glowing cavities of where the oxygen 3 data has been recorded. So these are absolutely great fun. But of course, the downside to that is there is an element of expense, as there always is, an element of expense when you're sort of setting up and maintaining your own equipment. Because not only do you have the equipment costs, which will inevitably run into many thousands, but you also have the monthly hosting fees as well to get the people to sort of look after your equipment out there. So the other alternative, and this is something I had first-hand experience with for about the last year and a quarter, using a platform called Telescope Live. Now, this is where you actually pay to observe with their telescope. So you'll queue a proposal to one of the telescopes, and when the image is taken, it sends you your data, and then you download it and you can process it. And I have 3 observatories, one in Spain, actually next door to where Ian King and I have ours at the same location. One in Australia, where they have a small FSQ 106 refractor, and one in Chile, which is where they have the lion's share, I should say, of the telescope. So we'll have a quick look at some of those. But for now, this was one of the first images I took, actually from the Australian telescope, of the Large Magellanic Cloud. You can see here. And within that is this incredible object, the Tarantula Nebula, which became famous in 1987 as the site of, or near to it, of the first sort of naked eye supernova. Unfortunately, we couldn't see it from the Northern Hemisphere. We can't see any of this object from there. So this was just a sequence of short exposures. And I was really sort of intrigued because the resolution's great with this incredible field of view under dark skies. You know, the guiding and everything's really good. So I was kind of hooked straight away. But we now jump straight into the deep end, shall we say. And I'll show you a picture of their largest telescope, which is actually a 1 meter monster on an alt-azimuth computer controlled drive. Now, as you would expect, time on this could be quite expensive and is certainly sought after. A lot of it's allocated to research work. But quite early on, I was able to take a picture I was very pleased with, which is the lovely galaxy NGC 1365 in Fornax. This is a famous galaxy because you pick up the astronomy books from the 60s and 70s, you'd open it up and you'd see pictures, probably black and white actually, but this one's got some really, really nice resolution to it. They have what we can laughingly call an intermediate sized telescope, in this case a 24-inch plane wave. This is probably their most popular telescope. I used it quite heavily last year before it became too popular, and I was very, very pleased with the results. In fact, I showed you a part of this one earlier on when I was talking about the Topaz software. This is our old friend, the Eagle Nebula, and the Pillars of Creation. And if I just zoom in on this, again, I think you can see that this that telescope and the CCD camera and filters, they use Astrodon filters, it's produced an incredible image, I think. I was very, very pleased with this one, particularly applying the Topaz software to almost deconvolve the image. I was very, very pleased with this. And I think out of all the pictures I've ever taken that I've placed on my Flickr website, this has had more views than all of them. More interesting targets as well are this, which a lot of you won't be familiar with. I certainly wouldn't be. This is NGC 3324. It's a target that's actually right on the edge of the Eta Carina Nebula. And I will show you an image of that right at the end of the talk in a couple of minutes. And this makes a really nice target in its own right. And once again, this illuminates everything that I've been saying about the Hubble palette. The pleasing colours, but also the fact that it gives you this lovely sort of three-dimensionality. This, when in this orientation, that almost reminds me of like a hood with this sort of weird sort of texture inside. It's a very interesting target. And if I remember, I'll show you whereabouts this is in the Eta Carina Nebula in a slide to come up. And while we're on the subject of exotic targets, I mean, have a look at this. This is NGC F3576 in Carina, a very exotic object by any standards. It has, as always, a popular title of the Statue of Liberty Nebula, and it's one of a kind, I think. I don't think we have an equivalent to that in the Northern Hemisphere. It's got these incredible sort of arching loops of nebulosity, the dark nebula that makes up the so-called Statue of Liberty, but also down here, amazing three-dimensional structure. And to be honest, although this was taken with the 24-inch telescope, it's only, I think, 3 10-minute exposures per filter. So again, this is another reason why remote systems where you just buy time on these telescopes, because they're in such good locations, under such good skies, and with really good instrumentation, that you can get fantastic results just taking short exposures. Just on to the next slide. Another one taken with the 24-inch, needs no introduction, I'm sure. This is the Helix Nebula. This is quite a deeper exposure this time, and I actually binned the CCD into a 2x2 configuration, because even with that configuration, the sampling rate is still under 1 arc second. And I've done that because I really wanted to try and capture the sort of exotic cometary globules that emanate from the central white dwarf star. This is a planetary nebula that's collapsed and exploded or puffed its layers into space, and the cores collapsed down into a white dwarf. And you get this nice kind of color contrast between the central cavity in the blue and the red structure of the nebula itself. And if you look carefully, you'll see lots of little faint galaxies just sort of scattered across the field, some within the envelope, or apparently within, not really, in the line of the envelope. And there's even a couple in here as well. So that attests to the great quality of the sky in Chile. And using one of their other telescopes earlier this year, the 20-inch FAST f3.8 corrected reflector. These are my favorite telescopes out there. This is a close-up of the Rosette Nebula yet again. And look at the wonderful resolution contained within these dark dust, the Bok globules, and the structural jets within the center of the nebula. Also taken with the same telescope is this, which is a very deep image of M78 in Orion, a wonderful object to image with this telescope. These are actually only made up of 3 10-minute exposures per LRGB filter, so overall relatively short exposures. And this one was actually afflicted, the 3 10-minute luminance frames were afflicted with 6 satellite tribes, which is very unusual for the Chile Observatory. And there was just this big burst of them, but I was able to use a couple of different techniques to remove those from the end result, which I was very pleased with, because it's a very, very nice result. And another one of my favorites here is our old friend, the Witch Head Nebula, not in its entirety, and it looks more like a sort of a spooky ghoul here than a witch head. But the idea is when this is turned sideways on, this would be her eye, and the nose and the sort of the chin and the mouth and everything. And she's sort of staring balefully at the bright blue star Rigel in Orion. That's why she's blue. This is a reflection nebula, so the light of the nebula is just reflecting the blue light of the luminary Rigel. And then just to finish off with a couple of brand new images, or 3 possibly, taken just in the last week or so. And this is with another telescope that they've just recently unveiled in Chile, which is an 8-inch f2 telescope, so a really fast telescope. So I've just included here to finish up with a few of those images. These are 5 10-minute exposures per 3 narrowband filters. So this is, of course, the Lagoon Nebula here and the Trifid up there. This is pure narrowband. This one here, very exotic target. This is NGC 6188, the Fighting Dragons of Ara, they call this. Another one of these sort of preposterous names. And again, this is just with the f2 telescope, and these are just 5 10-minute exposures once again. You can see with this incredible wide field of view, okay, just kill that. With this wide field of view, it's captured billions of stars, and the gas and the dust. This is a wonderful system to use. And I think the last slide of the deep sky stuff is one of my favorites. This is the Eta Carina nebula that I talked about earlier on. We can't see this from the UK, but if you remember the target I showed you earlier on 3324, that's it up there in the same orientation. So with a telescope like, you've got a choice of lots of different telescopes that give you, different fields of view and the like. So I hope you've enjoyed looking at all of the different slides from the very first astrophotograph up until what we can now do today. Okay, it's not our own equipment, but I assure you, you cue your target, you can censor it how you like, you get the data, and you can make it your own image at a cost. Finally, if you're interested in any of the techniques that go into this, a tiny little advert just to finish off with. This is still available for astronomy now. It's my third book on image processing. This is the sort of contents page. You can get an idea of all the stuff that's going in there. And if you're interested in all the narrowband stuff, have a look at that. There's a lot of stuff in there. That's it. That's the last one. Thanks very much.
Thank you very much, Nick, for that run through how you too can pretend you're a professional astronomer. No, I say that because many years ago, my father had bought the Reader's Digest Great World Atlas, and the section on astronomy included this huge double-page picture of Jupiter, which it said was probably the best image of the planet that anyone had been able to obtain. And now pretty much anyone in the country can take a picture better than that from their back garden without needing a 100-inch telescope. Though Matthew has put in a question, he says, I know you haven't talked about webcams, but do you have any recommendations for a cost-effective webcam for astro use?
Well, I don't, because I don't use them, but there are a lot of people out there that are, and there are certainly a lot to choose from. So I think I'd recommend have a look on something like Stargazers Lounge, the sort of online forum, and you'll talk to a lot of people that are doing great work with webcams, really spectacular work. As Jerry said, if you look at, for example, at the top of the food chain, people like Damien Peach, not only are they better than the images that the professionals were taking back in the day, but they're like much better. They're kind of getting into the sort of Hubble area now, which is spectacular. And I tip my hat to these guys because it's a different form of astrophotography. But if you stick at it, and like Damien, you'll just get world-beating results. So just check online. There's talk to the dealers as well. People like the Widescreen Sensor, Flow, all these people. They'll advise you on that.
Okay. Thank you very, very much indeed, Nick, and do everybody keep a lookout for his articles, and of course, do buy his books as well. Fine, so we now move on to our final speaker, and I have to say that I was incredibly pleased to be able to get hold of him to talk to my Astronomical Society just shortly after Perseverance had landed on Mars. Let me just come back to here, and he is no less than the lead program executive at NASA HQ for the Mars 2020 mission. And so he's currently 5 hours behind us. But he's also the in charge of Mars exploration overall for NASA. We could hardly get a greater expert on this subject. I was hoping that he'd be able to give us the results from Ingenuity's first flight, but we'll have to wait just a little bit for that. But meanwhile, to hear all about the exploration of Mars, George Tahu.
We'll go for sharing.
Yep.
The presentation. Okay, so do you see the title slide?
We do, yes.
And video is okay?
I can see you at the side.
Okay, well, great, then we'll get rolling. So thank you very much for inviting me to join your group today, and really excited to tell you all about what we're doing at Mars right now. As Jerry mentioned, we landed our latest Mars rover on February 18th, an incredibly exciting day, I can tell you. Perseverance is now on the surface, and I wanted to share a little bit about how we got there, why we're doing this mission, and what we're looking to do in the future in sort of Mars exploration. So if you look at Mars today, it's a very cold, dry desert. This is a photograph taken from our previous rover, Curiosity, which we sent about 10 years ago. And, from all the other missions that we sent to Mars, we find that Mars does have some characteristics of a potential habitable environment. We've been trying to build up our missions slowly to try to understand that question. Could Mars ever have been an abode for life? A lot of the reason we're asking that kind of question is because through the missions we've sent, we believe that Mars billions of years ago was much more like Earth. Mars and Earth had very similar birth stories, both formed in the swirl of the solar system formation, and about 3.5 billion years ago here on Earth, that's when we started to see the evolution of microbial life. And if Mars had potentially surface liquid water at that time, if it had other aspects of its environment that could have made it conducive to life, that raises a big question. Could life have taken hold in that ancient past? So we try to answer these and many other questions about Mars by sending our robotic craft, which we've been doing for many decades. Certainly even began in the early space age, and we've progressed from being able to do flybys in the early years of the space age to then doing orbiting, then finally landing with the Viking landers, and then evolving to being able to rove, move around the surface. And we've been increasing our capabilities as well as our ability to learn, answer new science questions as we go. So this graphic shows kind of the latest past couple of decades in our modern Mars exploration program. Many of the missions here are already completed, such as the Spirit and Opportunity rovers and the Phoenix mission, but the rest are there at Mars. So there's actually kind of a nice fleet of Martian exploring craft, both sent by NASA and also sent by other international explorers. So the European Space Agency has a couple of craft, and just this year joined by some new players, the United Arab Emirates with their orbiter Hope, and China with their Tianwen-1 orbiter, and hopefully soon their landed craft in the next few months. And we're looking beyond. Other nations will join. JAXA has the Japanese Space Exploration Agency is looking to explore the moons of Mars, and both the, of course, European Space Agency leading up with their ExoMars rover, Rosalind Franklin, and both China and NASA are looking to do Mars sample return missions. So it's an exciting time for Mars exploration. So back to Perseverance. This is really the first step of what we envision to be a Mars sample return campaign. And we're doing this with our partners in the European Space Agency. So Perseverance is that first step. It's the sampling activity to get to the surface of Mars, to collect a very compelling and scientifically returnable set of Martian samples that we can put into tubes that look about like this. This is the model of the shape. We can fill it up with a our rover has a coring drill, so we can take a core sample about the size of a small piece of chalk or crayon. And we have 43 tubes of these on board the rover that we can take samples and then leave them on the surface for the next set of missions. So the next set of missions would be jointly done with ESA, with the European, what we call the FETCH rover, and the NASA-led Mars Ascent Vehicle is the rocket. So the FETCH rover would go collect these sample tubes, bring them back to the lander, load them up into the Mars Ascent Vehicle, the small rocket, launch those into Martian orbit. And then the third vehicle is an orbiter that ESA would develop with the NASA-provided sample capture and rendezvous and the Earth entry vehicle systems. Grab that sample container, then it would use solar electric propulsion to spin out of Martian orbit, come back home to Earth, and eventually land at the Utah desert here in the US. So it's quite a grand campaign, and we are now, this is something that the Mars science community, broad planetary science community, has been looking to do for many, many decades, and now we're actually embarking on it. So it's quite the adventure. Now, where do we want to go, right? And what are we looking for? So this is an image of the Gale crater environment where the Curiosity rover is currently exploring. And the key, one of the key astrobiology questions that Curiosity had to ask was, did Mars even just have an environment that was capable of sustaining an ancient microbial life? And fortunately, the answer is yes, at least from Gale crater, what Curiosity was able to find, there was an ancient river system or lake bed in that Gale crater, liquid water that was not too acidic and not too salty. And we found by studying the rocks there that there were the key chemical ingredients for life that could be present: carbon, hydrogen, oxygen, phosphorus, and sulfur. So it's a tantalizing possibility that, okay, if it had the environment, now the next question is, let's actually see if we can go look for any kind of direct evidence of ancient life. And that's what Perseverance is looking to do. But what should we look for, right? We're not looking for complex, large fossil type things like we might find on Earth. Those are the left-hand images you see, macro fossils like, creatures or plants. What we're looking for is more what you see on the right-hand side, signs of ancient micro biosignatures. And a biosignature is something that could be indicative of life, whether it's a chemical signature, mineralogy, even just the structure, the pattern, the morphology, evidence of organic molecules. Those types of things is what we've designed Perseverance to go seek out. And this image is a picture of a over 3.5 billion years old stromatolite found in the Australian outback. And the science community believes that this is the type of thing that might most likely be found on the surface of Mars if we can find a landing site that is of that age and be able to get to rock outcrops to actually study them. So that's what Perseverance is designed to do. So how do we get there? We have to launch at the right time. Earth and Mars going around the sun get close to each other about every 2 Earth years, right? So that's the optimal time to launch, because you want to use the least amount of energy for your launch vehicle. That way you can have more mass and less cost to send a vehicle on a trajectory like that. So we launched here in July this last year. And when we launch, we don't aim directly at Mars. We have to aim where Mars is going to be, much like a American football player might throw a pass to a receiver down the field. And took us about between July here to February to follow that trajectory, taking all the energy to get there is really given to us by the launch vehicle. And most of the way is coasting. We do have small thrusters, and we can make the acronym here, TCM, is Trajectory Control Maneuver. We actually only had to do the first couple ones. The last few, we were so well on target, we didn't have to do the last few maneuvers. So the navigation team did an excellent job getting us towards where we wanted to be. So to give you a sense of how our capability has evolved over the years, you know, we couldn't just design Curiosity or Perseverance class rovers from scratch. We had to learn. We had to build up our capabilities, and that started with the first tech demonstration of roving on another planet, and that was the Mars Sojourner rover that rode along on the Pathfinder mission in 1996, landed in 97, and that demonstrated, yes, it's possible to actually move around on the surface and maybe conduct science. So a few years later, we built upon that, built the Spirit and Opportunity rovers, and made them effectively robotic geologists. They carried a small rock abrasion tool on the end of its arm, small hand lens like a geologist might use, and a small X-ray spectrometer on the end to be able to move around and actually explore two very different landing sites. And of course, to do the next set of big questions, those astrobiology questions, we needed much more capable rovers, much more capable science instrumentations, and that's what led us to the Curiosity class rover you see right there, the size of a small car. And Perseverance, if you were to see them side by side with Curiosity, looks pretty much the same. And that's by design, of course. We wanted to leverage that heritage, leverage the designs, the things that worked well, but make the improvements where we needed. And so really Perseverance is a great next step in our capabilities of what we can do to explore. So this mission has 4 key objectives. First three are all around that searching for ancient microbial life. First, you want to do the geology. You want to land, take a look at the context of where you are, understand the different geological units, and where would be the best place to actually go up and do some sampling and some close-up looking with the what we call our contact instruments on the end of our robotic arm to actually interrogate some of those rocks and find which are the best ones to actually take a rock core sample and put into our sample cache. So those 3 objectives. Now the 4th one is something that we've done throughout many of our other missions. These parallel the overall goals that we have for our robotic exploration program. The question of life, could it have evolved on Mars? What's the climate like? And what is the geology of the actual planet itself? How did Mars as a planet evolve? And what can we learn not only about Mars itself, but other planets in the solar system, as well as our own home? And that 4th objective is someday we do want to be able to send human explorers to the surface of Mars. So we try to build in as best we can, any of our missions, some component that can help us prepare for humans, whether that's taking data or doing technology demonstrations. We have a couple of key ones on Perseverance. So here's an artist concept or modeling of our rover, and a few pointing out to the 7 key instruments that we have, as well as our sample caching system on this. I'll go kind of clockwise around, starting with the very first ground penetrating radar that we're able to have, and this is contributed by our partners in Norway, and it's called RIMFAX. Then it's starting at the top of the rover, the masthead. We have our next generation mass cameras. These are the high resolution cameras. And these are evolved from Curiosity in that they actually have full zoom capability. Curiosity actually carried their 2 cameras were 2 fixed focal lengths. But now we have 2 identical zoomable cameras to really take high resolution imagery and a little bit of video too. Now up at the very top of the mast is what we call SuperCam. And this is a laser spectrometer that is built jointly by the US Los Alamos National Laboratory and a consortium of French space agencies and research institutions. And this is effectively a laser that we can use at a standoff distance, fire it at some rocks, and when the laser hits the rocks, creates a plasma, and that large circular telescope at the top can actually look at that plasma created and determine the components of the rock. And that gives us a way to actually, from a standoff distance, firing the laser, get a better sense of which ones would we like to spend the effort to actually rove up to, and then use the instruments at the end of our robotic arm. Then on the down from the mast, along the neck of the mast and little other parts on the body of the rover, various sensors that make up the meta weather station provided by our partners in Spain. This takes temperature, pressure, humidity. There's also a small camera looking up that's studying the dust environment, a little bit of radiation measurements. So it's all encompassing environmental monitoring station there on the surface of Mars. Then on the end of the robotic arm, we have the Sherlock. It's another type of laser spectrometer, ultraviolet laser. And of course, if you have Sherlock, you have to have his partner Watson. That's the next generation hand lens close-up imager at the end of the arm there. And then the Pixel X-ray spectrometer. And through Sherlock and Pixel, we can do very close-up both imaging and chemistry analysis, as well as mineralogy. Now, the other big thing through the middle between Sherlock and Pixel, you see that kind of round circular part, that's our robotic coring drill. It's a rotary percussive drill. And this is an example of, it's a 3D print of one of the drill bits. And you can see it's a hollow, such that we can take these sample tubes, they go inside the drill bit, so that when we drill into the rock, that sample is going directly into the sample tube. Then we're able to, the robotic arm goes to the center of the rover, to the what we call the carousel. It rotates, unchucks this bit, brings it inside the rover, where there's another smaller robotic arm that pulls out the tube and then moves it to the various stations to seal it up and then leave it on the surface of Mars. Moving on, lastly, in the body of the rover, this is one of those tech demonstrations I mentioned for preparing for future human exploration. It's the MOXIE oxygen generator. It will suck in part of the Martian atmosphere, which is largely made out of 98% carbon dioxide. Pump it across a catalyst at high temperature, and it can split the carbon dioxide molecules into oxygen and carbon monoxide. So we have sensors on there to be able to measure both the purity and the amount of oxygen that we can generate. This is called in situ resource utilization, or learning to live off the land. And if this technology works as we plan, it could be scaled up and potentially provide the type of supplies there on Mars, rather than us having to bring large amounts of oxygen supply when we try to send human exploration systems there. We can generate the oxygen on the planet of Mars rather than having to drag all of it with us. So that's an exciting demonstration we're looking forward to in the coming weeks and months coming up. So to get all this together, of course, it quite a lot of time. We started this whole mission in around the 2013, 2014 timeframe. Spent the first couple of years doing the design, but since we had a lot of heritage from Curiosity, we were able to jump right in and do a lot of the systems build to print, the back part of it, the cruise stage and the aeroshell. Once we had all these systems put together, then we have to test them, put them through the rigors of space exploration, temperature, pressure, and the extreme radiation, and then build up the rover. Bring all that together, then also do the testing of the rover itself as best we can here on Earth. Now, we can't test the entire flight system like we might like to do. That's pretty much impossible to totally simulate landing at Mars, but we can do as best we can. We want to test all the flight systems, the sampling system. That's probably the most complex system we have ever built to send into space, this sampling system. So once we have it all together, then we get it all ready, pack it all up, and ship it to Florida at the Cape Canaveral Air Force Station, where we plan to launch. All of this building and putting it together largely took place at the Jet Propulsion Lab in Pasadena, California. And of course, it takes an enormous amount of people to do this kind of work. We had over 2,000 people, both at Jet Propulsion Lab and the other NASA centers across the US, over a team of over 400 scientists, as well as thousands of contractors, not just here in the US, probably through 44 states, 560 cities across the US, but we also had contractors and partners through 14 different other countries. So it was quite a worldwide effort. And as many of you, of course, when the pandemic hit last year, we had to learn to do things very differently. It hit right about the time that we were packing everything up from Jet Propulsion Lab and shipping everything down to Florida. We were able to do that safely before things got too hot and heavy here with the pandemic, but we had to shift the way we do things. So really, we moved to a situation where about 80% of our team was able to be working out of the home. Of course, there was folks that had to do the hands-on work, and we put in place a lot of new types of protocols to make sure that everybody could do this work safely. But of course, it wasn't just our team that we relied upon to enable them to do what they needed to do. It really took a much broader team, their friends, their families, to provide the support. And also another huge community, and that's the healthcare community and the medical community and the frontline workers who really enabled all of us to do our job. So because that was so important to us, last summer, the team decided to come up with a way to honor healthcare workers and frontline workers by putting this plaque. You see an image of the plaque on the left. It's a symbol of the Earth with our vehicle launching and heading towards Mars. All of that supported by that community, represented by the rod of Acephalus with the serpent around the staff. And we mounted this plaque on the side of the rover, on the port side towards the rear, and that is now on the surface of Mars. So we hope maybe someday if future explorers come across and find Perseverance, they'll know really who it was and the community that took to enable us to do what we needed to do. So once we had all this equipment down at Florida, we'd pack it up from top to bottom. We call the cruise stage. That's the propulsion and the heat rejection system that keeps our system healthy on the way to Mars, does those trajectory control maneuvers. The rover is protected by the aeroshell, that's the back shell, and then the heat shield on the bottom. You can see the rover tucked up underneath. And as this was packed up, once this got put all together in Florida, the next time it would ever come apart is when it's doing its entry, descent, and landing at Mars. So we take that full spacecraft, put it in the fairing of the launch vehicle, roll it out to the launch pad. Large crane puts it on top of the launch vehicle, and then roll that launch vehicle out to the launch pad. Of course, our team had to do things a little bit differently due to the pandemic, spread out a little bit more. And but there's one tradition we still wanted to keep that's been going on since some of the early missions that JPL flew, which is it's a tradition to share peanuts for maybe think of it as good luck. Normally, you pass around a big jar of it. This year we had to do things a little bit differently. Everybody had their own individual packs, but they're definitely an important part of any planetary mission. So our launch was July 30th, went off beautifully. It was a great morning, and our partners at the United Launch Alliance, who do the build and launch the Atlas V launch vehicle, gave us a terrific ride and got us on our way to Mars. So how did we choose where we're going to go? This was actually a multi-year effort with the broad science community. We had several years of where we invited the community to propose landing sites that would be able to meet those mission objectives that I talked about earlier. So this map shows the white spots are places where prior missions have gone. The yellow spot identifying where Jezero Crater is if you had a map of Mars laying it out flat. So why Jezero Crater? Jezero is a really interesting place. It's a crater that once held a lake, and there are a lot of craters on Mars that could have hosted lakes, but not every crater is the right age that might have the right type of geology to prepare to preserve those biosignatures I spoke of earlier, the potential evidence of life. And at Jezero, it's a unique place where there was an inflow channel where where water was filling up the crater with a lake, and an outflow channel. And that inflow created this river delta structure. So, and here on Earth, river deltas are places where you can find lots of evidence of life. You go scoop up some mud, you'll get all kinds of critters in your hand. So this is the type of place that we'd really like to go to look for that evidence. So once we get to Mars, we're screaming in towards the planet at about 16,000 miles an hour. You got to slow down in a matter of about 7 minutes. That's how long it takes to get from the top of the atmosphere down to the surface. So we followed the same type of entry, descent, and landing technique that Curiosity pioneered. We call this the sky crane approach. We come through the atmosphere. The heat shield protects us first from that all the friction from hitting the atmosphere, and that shaves off about a 0 order of magnitude from our velocity, slows us down from hypersonic down to supersonic speeds. Then we pop a supersonic parachute to get us down to subsonic speeds. But the one thing we added with Perseverance is a new landing technique we called terrain relative navigation. Actually, two landing techniques. One was a new technique on when we pop the parachute that helped us narrow our landing error ellipse, so we were able to land in a much smaller area. And then the other one is this hazard avoidance capability, terrain relative navigation. As we're coming down, we're taking photos with a camera facing down, and we're comparing that to a map that we have on board in the computer that we built up from the orbital imagery. And that map, we had marked out areas that were potentially hazardous, whether it be slopes or sand dunes or large rocky areas. As we're coming down, we have a capability, once we detach from the parachute, we have a rocket pack, basically, that is on top of the rover, and that descends us down and slows us down to just a few meters per second. But we have a capability, once you let go of the parachute, you definitely want to make sure that parachute doesn't land on top of you. So we have a divert maneuver. And what we're able to do is take advantage of that divert maneuver. And when we do it, take a look at where we're coming down. And if we're coming down at a hazardous area, we can divert in a direction that's more towards a safer area. That's the terrain relative navigation. Then once we get close to the surface, the sky crane maneuver lowers us down on some nylon ropes. The wheels are then deployed. Once the wheels set down on the surface, it cuts the ropes. The sky crane flies off. So having described that, now I want to show you a little bit of video. This is a combination of computer animation to show you what's happening, what I just described, as well as the actual video of the events, seeing how some of our team reacted. And one other thing we did with Perseverance we'd never done before. We put on board some ruggedized commercial small cameras that we could try to look at the parachute as it deployed, also look at the rover as it's coming down, and looking up at the sky crane. So many of you probably have already seen this, but it's definitely worth trying to go through again. So this was February 18th. Hopefully this will play.
Propulsion, go. EDL safely, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry in our space. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. The parachute has deployed, and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. The sky crane maneuver has started, about 20 meters off the surface.
Tango Delta, nominal. Touchdown confirmed. Perseverance safely. Ready to begin seeking the sands of past life.
So I hope that played okay. Hope it wasn't too choppy. So here's that image. As we are landing, looking down from the sky crane, looking at Perseverance as it comes down. And this is the first image ever of a spacecraft landing on another planet. So where did we end up? We were targeting as close to the river delta as we could, but as we came down, that terrain relative navigation found that we were headed towards some hazardous area. You can see on the right, that's that blue and red image there is of the red is like, those are the hazards. So we don't want to land there. We want to narrow in on these blue spots. So terrain relative navigation definitely did do a good divert for us and put us right on the other side of that green geologic unit that we've identified on that map there. And we've dedicated, named our landing site Octavia E. Butler Landing for a prominent science fiction author that's written many books, inspiration and to our team. And now the team is trying to figure out, all right, where are we? What kind of geology do we see around us? And starting to think about what path do we want to take to get to that delta and start doing that sampling campaign. So they're thinking about maybe doing a counterclockwise move, towards north and west, or maybe clockwise down south and then around that other unit. Reason they're not looking to go straight across is that unit that was between us and the delta, lots of sand dunes, and we don't want to get bogged down and stuck in a sand trap. So we're looking to go around it. So if you were to stand on top of Perseverance today, this is shortly after we landed, this is what you would see. And you kind of see right there in the near distance, a lighter patch. That's where some of the dust was blown off of the surface of the rocks from the sky crane as it came down. You're starting to see the canyon rim off in the distance. And as we swing around, you'll see there's another patch where on the other side of the rover, where the other side of the rocket thrusters were really blowing away a lot of the dust on the rocks right there. And as we swing around here and come towards looking back towards the rear of the rover, now you'll start to see the nearby outcrops of that river delta, the lower rims there. So that's where we want to head off that direction. So we've been, it's been a month, a little over a month there on the surface. We've been doing what we call the commissioning of all of our systems, making sure they work properly, doing some drives. And so this is just a smattering example of some of the images we've been bringing back. The one in the top middle I wanted to highlight in that all these instruments work together. So we have, again, the context images, instruments up at the top, SuperCam and MassCam, providing that knowledge of, where are we, what do we might want to look like. SuperCam also has a telescope type thing to really look up at rocks to get a very close-up look from a distance. That's what you see, that inset image. The one on the top right, this is a look at what we call the workspace right in front of us, where Perseverance is right now. We have driven around and found a place that we're going to sit for about the next couple weeks, because we have an exciting technology demonstration coming up. Now, before I move on to talk about that, you may hear a noise. This is the sound of the rover driving. I mentioned those cameras that we put on for the very first time, the ruggedized cameras. One of the other things we use, commercial off the shelf, is a microphone. First microphone to successfully operate on another planet. And that's what you're hearing. The wheels turning, a little bit of the whine of the rover itself, and crunching of those rocks as we drive across the surface. So this is the very first selfie photo that Perseverance took. The way it does this, it sticks its robotic arm out front, turns it around, and that Watson imager looks back at the rover. So that's why you can't actually see the arm in the image, because it's, you can't see your own arm when you do a selfie, or at least hopefully not. But you'll see that to the small thing in between the rover tracks to the left, we've dropped something. This is our next technology demonstration. That is the Ingenuity helicopter. And it's a really exciting technology that we added to this mission. You don't get to go to Mars very often. And when you do, you want to maximize what you can do with it. So just like the Sojourner rover was a technology demonstration on the Pathfinder mission, and it set up all the capabilities for all these future rovers, Ingenuity is also a tech demo that could potentially open the door for future aerial vehicles to explore Mars. So it's Ingenuity is, the body of it is about the size of a tissue box, and it has these two counter-rotating rotors. The rotors are about 1.2 meters in length, and have to spin at an incredibly fast, over 2,000 RPM. Flying on Mars is extremely difficult. I mentioned the atmosphere earlier. It's very thin. It's only about 1% as dense as here on Earth at sea level. So that'd be like trying to fly at 100,000 feet here on Earth, and where commercial airliners are flying more at 30, 35,000 feet. And I think even the record for a rotorcraft is only to like 40,000. So it's extremely difficult with that thin atmosphere. There's not enough molecules to push against to get lift. So you've got to have super lightweight craft, high speed rotors. Because the temperature on Mars is extremely cold, into the negative 100 degrees Celsius, you've got to have heaters to keep it warm. The top panel is the solar panel. It's got to be able to charge itself, keep itself warm now that it's left the safe protection of the rover. And it's also got to do all of this autonomously. Because of the time delay it takes for radio signals to get from Earth to Mars, there's no way to joystick this from Earth. You've got to load up all the commands and have this thing have the smarts to be able to fly itself all on its own. So another challenge was, how do we get this thing on the surface? We had to find a way to fit this on the belly of the rover in a folded up condition, and create a deployment system that could set it down gently onto the surface of Mars. That's where you're seeing the test video of us doing that on the bottom. And of course, at the top there is animation of what we hope the first flight might look like. You may have heard in the past week, we had hoped to have done the first flight, but we did run into an issue with the software. Ended up being a timer on the helicopter was preventing it from moving in from pre-flight mode to flight mode. So the team has been working through a couple of options, one of which is kind of a patch or a workaround for that timer. And we've actually uploaded that and tested it 2 or 3 times on the surface of Mars. We were able to get through just yesterday, completed a test of a high-speed test of the rotors. So now we've been able to move into the flight mode, spin the rotors at high speed, and we're looking at when we might be able to set a first flight attempt. The other option is we could upload a whole new set of flight software. That takes a little bit more time. So the team has been looking at it, weighing the risks, which is the better path. So hopefully we'll be able to pick a path and choose a direction very soon. So this is Ingenuity on the surface now, a picture from our Mastcam camera. And you see on the right, that's an image of the slow, not the high speed rotor test, but the slower speed rotor test that we had done on April 8th. So Ingenuity has, we have a 30-day window of time on Mars to be able to do the flight tests. Hopefully we would plan to maybe do as many as 5 flights, since we've had to use up some of our schedule margin. Might be a little less than that, but we'll fit in as many as we can. After that flight campaign, it's now time to move on to the primary mission for Perseverance, which is seeking out signs of life. So this is an animation of what it takes to do this very complex sampling situation. We use the robotic arm, outreach to the rock outcrop that our science instruments have defined as a best choice to try to drill. We do that drilling with that drill bit, getting into the rock, pulls it back, and now we're going to dock with that carousel on the front of the rover. In this fashion, the drill will unchuck that drill bit. It gets rotated down in the carousel into the rover of the body of the rover. Then a secondary small robotic arm inside will extract that tube and then move it over to a station. We're going to do several things. The animation doesn't show all these sequences, but we do a volume check to make sure we actually have something in there and how much it is. We have a small camera that can look inside the tube and see what we've got. Then we do a sealing operation where we plug it with a plug, which creates a hermetic seal. Then we can move it back to a storage rack. This is where we have the tubes, the 43 tubes stored. And now we can store it until we're ready to drop it onto the surface. And off we go with science. Now in that video I showed, hopefully you noticed the real imagery of this is the parachute on Mars as it's deployed. And you'll notice it's got an interesting design on it. Oftentimes, parachutes will have this kind of design. It helps the engineers be able to understand how the deployment operates. And actually not only for just, hey, it looks cool, but a large driver for why we put these cameras on this mission is, even though we've landed successfully several times before and our parachutes have clearly worked, we really don't know how well they work. We had no idea how the parachutes might have inflated. Were they really doing it properly? So we wanted to try to get that kind of data to help us design future larger parachutes for other systems. But this design, when I saw this, I said, that's quite a complex looking design. I wonder if JPL might have done something like they did before. With Curiosity, they kind of snuck in a surprise. On the wheels, they had some holes in the wheels that were done in a certain way, such that as Curiosity drives on the surface of Mars, those holes are creating a pattern in the surface, and it's a Morse code, ... spelling out JPL as it drives along. So as another surprise Easter egg, JPL put hidden in this design of the parachute was a binary code. And if you can decode that binary code, it spells out "Dare Mighty Things." And this is the motto of Jet Propulsion Lab that they use. And it's a nice message for both what this team has attempted to do and has now accomplished to get to the surface, the very ambitious mission that we have ahead of us, and hopefully, our mission, you know, I think you saw many of the reactions in the video. It's been a tremendous interest across the world, and hopefully we hope that provides a source of inspiration for everyone to dare mighty things, to persevere through many challenges that all of us have been facing this year, and hopefully reach some great accomplishments. So next up is Europe. Rosalind Franklin rover on the ExoMars mission, looking to launch in the 2022 timeframe. We at NASA are partners on that. We've contributed some components to the prime astrobiology instrument on board, and really looking forward to that one, to have yet another astrobiologist, robotic astrobiologist on Mars. So I hope that you can join us, follow along with the mission. Best way to do that is go to mars.nasa.gov. You can go to the Mars 2020 page on there. You can also follow us on social media at NASA Persevere or at NASA Mars, and follow us along. Hopefully in the next coming days, we'll have, looking for when we're looking to do the first flight attempt of Ingenuity, and having a great mission. So I will stop there. Thank you for letting me be here and sharing what our mission is all about.
Thank you very much indeed, George, for that superb run through of this absolutely incredible flight to Mars. And we look forward to many more in the future. We do have a few questions for you. One goes way, way beyond that, asking, are there any plans to explore the gas giants?
Gas giants. So
Yes.
as you know, we've sent a few missions out that direction. And so, and actually, I remember there was a question earlier about Pluto. Are we going back to Pluto again? So for the planetary science program here at NASA, we have sort of 3 different major categories of missions we do. One's the sort of the biggest, most complex ones, the most difficult ones we call large class missions, or maybe flagship class missions. That's like Perseverance. There's another one coming up that we're working on called Europa Clipper. And this is a mission to go to moon of Europa, which is moon of Jupiter, which is covered in ice. So it's going to be an orbiter that's going to study Europa, which many scientists think maybe that is another potential abode for life in the solar system. That underneath that ice crust, there might be a liquid water ocean. That could potentially be a place where life might be found. So we're going to do some orbital reconnaissance of Europa. There's another mission on board. Then back from the large missions, then the next one category, if you want to call them the medium class missions, we call them New Frontiers. And these are competed missions, but they're with a certain focus. We, about every 10 years, we poll the scientific community, we call it the decadal survey, and ask for what are the top priority science questions in planetary exploration. And the last time I did this, almost 10 years ago, now it's time for the next one. We're just getting that started up. But the last decadal survey set out a certain set of destinations that would be most interesting. And one of those is to the moon of Saturn Titan. So we have a mission called Dragonfly, and this will actually be, Ingenuity is maybe setting, the stage for aerial exploration. Dragonfly will take that next step. Titan, kind of, whereas Mars is, the environment is very hard to fly with thin atmosphere and low gravity. Titan a little bit easier. It's got low gravity, but a very thick atmosphere. So Dragonfly is actually a mission to send a fairly large quadcopter to the surface of Venus and be able to explore that area, as maybe that's another potential abode for life. So a lot of exciting missions coming up to explore the outer planets.
Okay, thank you. Someone has asked, will the samples stay in place with the wind on Mars? And I just simply warn everybody that The Martian, though very dramatic, is fiction.
Yes. Yeah, and even the author, yes, he noted, you know, hey, I got to tell a story. I got to come up with a way for something to happen, right? So you exaggerate. Yeah, the winds, while the actual wind speed, you know, maybe, you know, however many miles per hour, the fact that it is so thin, there's not much force. Now, there's certainly enough force to create, as we've already seen with Perseverance, dust devils. We see these every now and again, and you know, it certainly has shifts the sands, but no, it's definitely not going to blow away a sample tube. And another question we often get is, well, might there be enough dust that the sample tubes would get covered and they get lost, right? And the answer to that is also no. With the experience we've had with all our other landed missions, we are able to model very well the dust deposition. And if you look back at like some of the images of Spirit and Opportunity, you'll see, you know, their solar panels got covered. It was a thin covering. Now, for a solar panel, that can start to be a problem and start to reduce your energy output. But again, because there are enough winds, you get those dust devils that can't come by. We actually ended up getting what we called cleaning events. As dust devils would come by, they'd actually clean off the dust. So that's how Spirit and Opportunity were able to survive as long as they were.
Yeah, which answers another question that we've had. So thanks for that. Someone's asked, if the evolution of life on Mars was synchronous with the evolution of life on Earth, could areas such as the Tharsis region be indicative of hydrothermal activity around which life could have formed? But that's also relating to the tectonics of the Martian surface.
Yeah. Right. Which environments do you want to go look at to maybe look for a potential ancient form of life? And you know, we've never done actual age dating on the surface of Mars. You know, it's all very relative based, you know, crater counting, those sorts of things. It's very challenging to do in situ age dating, really. So, but from what we can tell from our orbital imagery and those types of things, a location more like Jezero was a place where there was geology that the science community believes was of that ancient time period. Honestly, I don't know whether something around Tharsis would be of that age time period or not, or whether it'd be just too young an environment to potentially have been habitable. The thinking is that, you know, while Earth and Mars started out very similar, Mars definitely changed a lot quicker. Smaller size, the fact that, you know, cooled a little quicker, lost, if it did have a global magnetic field, which there's indication there was, it lost it. So as soon as that happened, then solar winds started blasting the thicker atmosphere away. And so it was very quick in a geologic time scale where you started to lose that habitable environment. So that's kind of why we've ended up where we've ended up.
Okay. Now, the question about ingenuity. Someone has said that anybody who makes stools, or I could add anyone who milks cows, and that's not from personal experience, will know that you use a three-legged stool. So the question is, why does ingenuity run the risk of an unstable surface by having four legs?
It's a good question.
No.
I'm not really on the ingenuity team.
Well, they are flexible though.
They are pretty flexible. Yeah, they aren't stiff. So yeah, and you know, we did do testing here on Earth. When we developed Ingenuity, we both for just the flight component as well as that, can we land and take off, we would simulate it by, we put it in what we call the spacecraft simulator at Jet Propulsion Lab. It's a vacuum chamber. Pump out the atmosphere, then pump back in carbon dioxide at the right, pressure. And we even had it simulated where they built a wall of fans, basically, to simulate the winds. And we're able to test flight. We even had a small cable attached to the top of it that would do a little bit of gravity offset. So not, exactly simulating, but it got us to the point where we could simulate the lift that the Ingenuity would have to do in that type of thin atmosphere.
Okay.
And it landed okay. So
that's good. But along with simulations, I mean, something that really got me about curiosity when I first heard about the Sky Crane, that you're bringing something down on rockets and lowering your craft from that down, and you go until it touches the ground, and then the Sky Crane flies off. And the incredible thing about that is that you cannot properly simulate this on Earth, under Earth gravity and Earth's atmosphere. I mean, yeah, you can put it in a vacuum chamber and simulate the atmospheric pressure on Mars, but that is not going to be a few miles high, so you can do a drop test. This, I think, is an incredible testament to the people involved who calculated the engine power that would be needed to come down at a controlled rate to do this. And to know that they were saying, well, this is how it should work, but the only way they would know is when it was done for real on Mars. I think that's absolutely staggering.
Yeah, that's true. Yeah, when they first came up with that Sky Crane system, that I included, this is crazy. What are you talking about? But the more once you started really thinking through the engineering problems that you're trying to solve, you're trying to land, and it was brilliant in that, before we'd had these platforms that would, we'd land on a platform and the payload would be on top and it'd roll off, but then there was a lot more extra mass to have to do that. This was a way you were able to minimize the amount of mass you had to take. Plus, just deploying off of, Sojourner had an incredibly hard time getting off its lander platform. The little ramps, fabric ramps they developed, didn't quite work as planned, and they had to find a different way to get off. That was really complex. So wouldn't it be better if you can just land straight on your wheels? And so that's kind of how Sky Crane evolved. And yeah, but so we have to do tests as much as we can here in the Earth environment, and then do the rest by analysis. So yeah, it's incredible.
Of course, with Viking, which just had a single unit in each instance.
Yeah.
Once you've landed, all right, Viking wasn't a rover, but if it had been, you then have to carry the engines for landing around with you all the time. This way, you completely separate that mass, which means you need less energy to actually move around. So
exactly.
So someone's asked, is Ingenuity data going to be used for operations of Perseverance at all?
Probably not. We designed Ingenuity. It's a tech demo. These are things that we do at NASA to expand the possibilities of our exploration, right? And you've got to start kind of at this level. Now, if Ingenuity itself, it doesn't have any science instruments on it, but it does have two cameras. One black and white camera looking down, and that's for the flight controller to be able to look down and kind of gauge where it is. Then there's another camera just for for us humans, to look around. It's a color camera, kind of looking off to the side, a bit down. So hopefully we'll get imagery, from a high vantage point, which could be, we'll see what that looks like. Is it going to be stable enough such that, that kind of camera, and they, again, off the shelf commercial type small cameras, not unlike what you have on your cell phone. And, will you get a clear image or not? And what could you maybe learn from that? So who knows, if it could provide the science team with some kind of indication more from what they've already seen as we came down in landing. One of the other reasons for putting those cameras as we came down, we got a great view of our landing area coming down that really augmented what we can already see from orbit. So I think, the science team pretty much knows where they want to go. But you could envision in the future, maybe other rotorcraft that are designed for longer term flights. Ingenuity is not, it's really a short term design. That could you have robotic craft to follow along with a rover to do reconnaissance, or when you eventually have humans exploring, they could have aerial vehicles to explore. But I think one of the biggest advantages is aerial vehicles can go where rovers and probably humans can't. You could go to Valles Marineris and maybe explore the canyon walls and other places. So it's some great possibilities.
Okay, so what is the expected maximum altitude for Ingenuity?
It'll be, I think, the very first flight be about 10 feet, and then the next might go a little bit higher. So it's not extremely high, just several tens of meters perhaps. But as we get to the first several flights, if we have time to do the minimum, what we really wanted was to do 3 flights to get the data back, so we understand how the system works and that sort of thing, and what it's like to fly in that environment. Once we get those down, if we have the time, the idea is then to do some what we call exploration flights to really push the capabilities. So maybe we try to go a lot higher or a lot farther. We're really just going to be basing those on what happens with the first few flights and what we can learn and what we think makes sense.
Okay, thanks. Just have 2 more questions. One is, what method are they employing so that a future sample collector is able to locate the samples?
We're going to know exactly where these things are, right? We know as Perseverance drives along, we've got the orbital map. We know very accurately, within a year or 2, where everything is. So when the next mission goes that lands, again, it'll be a US designed lander with a European fetch rover on top. And we are going to use the same terrain relative navigation technique, but this time we're actually carrying a little bit more fuel in the landing system, such that when we do that divert and terrain maneuver, now we can actually guide to land where the samples are landed. So the idea, we have flexibility in how we do this. The idea is to drop all of these in a similar location. Now we could drop them as we go, but that would just make the job of the fetch rover a lot harder. You'd like to leave a depot of these tubes in one area, and we'd like to land as close as we can to that. So that's what that augmented terrain relative navigation will allow us to do. Then the fetch rover will be able to get up to it and collect the samples we need and bring them back to the lander. Okay,
and the final one says, George, are your lucky peanuts salted or dry roasted?
I think it was dry roasted.
Okay. George, thank you so much for your presentation. We've all really enjoyed it and, of course, learned so much about this. I'm just reminded, actually, looking at the image there, that someone else has sent a note saying that he admires your Lego Saturn V in the background. When it was reissued a few months ago, I bought one because my original was stolen, and I've been stuck in a hotel for months, and I thought, right, well, when I get a bit of time, I'm going to start building this and take a time lapse of it. And it's been 3 months later, and I haven't had the time to start it, but I do plan to. Thank you again. Nick, I can see that you are still with us. Are any of the other speakers there? Hi,
I'm
Nick.
still here.
Because I said earlier, I think that Martin Rees has had to go because he's presenting to some people in California. But Georgia, if you can stay with us for a few minutes.
Sure.
Then if anyone else has any other questions that they'd like to ask, we'd be happy to see them in the Q&A.
I had a question for Nick, actually. It seems for some reason that panelists can't leave questions in the Q&A. So while some of those questions are coming in, maybe a question to Nick. As some of you may know, I'm very interested in the potential threat that the mega constellations of satellites, obviously currently Starlink, but others later, are going to have on ground-based astronomy, and to some extent also orbital astronomy. Hubble is already showing signs of problems with the Starlink satellites passing across its field of view. Do you have any suggestions maybe on how amateur astronomers can mitigate the problem of the Starlink satellites?
It's possible. That there are two ways of addressing it. The first one is when you're actually stacking multiple images. I think as alluded to in the talk, if you choose images that don't have satellite trails on as a master frame, when you use these sigma reject algorithms to stack images, it can help to reduce them. If that doesn't work, then there are software methods, but unfortunately, it's kind of wallpapering over the cracks to an extent. It's just saving the data. You know, it makes it worthless from a scientific point of view, because once you start cloning and stuff like that, it makes the data less valid scientifically. You know, particularly if you're planning to use it for any scientific collaborations. So we can get around it. But you know, it's not easy, and it's not a good scenario. But I mean, you know, what we have to bear in mind is the bigger picture. You know, how are these satellites going to affect professionals, for example, that are looking for near-Earth asteroid threats and the likes? And bear in mind also there is radio pollution coming down from these satellites as well. It's not only a visual thing. So whilst you can accept that the reason these satellites are being used is a good one in terms of the global broadband and the like, in terms of the science, it's a big problem, and it will only get worse as well. So I mean, we're kind of the bottom of the food chain in that, you know, we sort of curse about these things, but we can deal with them to an extent. But it's a much bigger picture and a much more serious picture, I think. So it's you know, I'm not quite sure where it's going to go in the future, but I suspect it'll only get worse.
Yes, I think you're right. I mean, just as a little plug here, there's a talk I've been giving on the mega constellation thread. It's about an hour and 20 minutes long, and I've given it 8 times already. So if anyone else would like me to give the talk, then I'm quite happy to do so.
And having had Paul at my Astronomical Society doing that, I can recommend it firsthand. George, here's something for you. I well remember the Viking landings, and they each had 3 main tests that were done on the soil samples they collected and brought on board the craft. And for me, the most exciting one was the labeled release, where a sample was put in a container and a small nutrient was added. The idea is that if there were any live organisms in the soil, that they would take up some of this nutrient and release gas as a result. And this nutrient had a tracer in it, radioactive tracer. And by testing the result, you could see whether there might have been some kind of nutrition taking place. And the result from it seemed that, yes, there most definitely was. However, there was also a mass spectrometer on board the craft, which failed to detect any carbon. And so it was said, well, if there's no carbon, there can't possibly be life. And it was, I think, years later that it was discovered that the mass spectrometer was actually very badly flawed and couldn't have given the results that it was meant to. So if you ignore the mass spectrometer result, it seems possible that back in the summer of 1976, we did actually find evidence of life on Mars. I would love Gil Levin to be vindicated in this respect. Can I ask, what are your thoughts on this?
Yeah, I know that's definitely been a controversial topic, or not controversial, a lot of debate, right, in the science community. That is not my community. I'm more on the engineering side of the house, so I have no expertise to lend it, other than my understanding is that the beyond just what was going on at Viking, the broader community tends to, I think the consensus is that there was not a compelling evidence there. And, you know, what makes it really difficult in the search for life on Mars, particularly right at the surface, is, and why we've designed Perseverance to do what it's doing, is trying to look for clues of ancient microbial life. Not, there's no such thing as a tricorder. You can't say, you know, there's life, Jim, but not as we know it.
Yes.
You have to look at the pieces of the puzzle, and if all those pieces come together and put a compelling story together, okay, that's a maybe. But the large motivation of getting samples home is because we don't think that we can definitively say, I mean, unless we do see, you know, a microfossil, right? Or something just totally, you know, no question, but we don't expect to see that. We have to look at these potential biosignatures, the other pieces, clues of the puzzle, so that we can get the samples and then get them home, such that here on Earth we can analyze them with all the capabilities that we have here to a degree that you could never, at least, you know, in the near term, send that capability to Mars to do remotely, and even be able to, just like we have with the Apollo samples that astronauts brought back, they'll be here for decades and or generations even. And even the types of questions we can't even think of asking, much less answering now, the capabilities that we would have in laboratories here, you know, decades from now, will be able to interrogate those same samples. And so that's the motivation from the science community.
There is also the issue, of course, that Viking was literally scraping the surface, and the expectation is that life that had been at the surface may well have been killed off through radiation, which is why you want to go down below. As well.
Yeah, the surface is incredibly harsh. You know, not enough pressure for liquid water to survive. You know, which here on Earth, you got to have water for life. Could there be a different mode of life, you know, without water? Who knows? But then the intense radiation for billions of years, and the temperature regimes that there's, the consensus is, you know, surface, you're not going to find any extant life. But yeah, if you can get maybe below a few meters, below some of that radiation environment, and that's exactly what Rosalind Franklin is looking to do, right? It's got a deep surface drill, go down a couple meters. Hopefully that really works. And they have a way of actually analyzing the samples. It'll bring up samples, it'll bring up crushed samples. And then the MoMA instrument, the Mars Organic Molecule Analyzer, that's a German-led and US and Italian collaboration. Excuse me, US-French on the instrument collaboration with Germany. And that'll maybe be able to actually look at that deep sample in situ. Whereas we can't actually analyze our samples. We can analyze the rock before we take the sample, but once it's in the tube, it stays in the tube. So we can't actually analyze our sample until we get it home. Two very different ways of looking at it and going to a different landing site. Yeah, I see a question was in there about will Rosalind Franklin uses a sky crane. No, there will be a parachute. And in fact, that's a European designed parachute. You know, a couple of years ago, there was the tech demonstration for the European lander, the Schiaparelli lander. Unfortunately, that wasn't successful, but as I understand it, they think they know what went wrong and have made some improvements with the parachute. But it'll be a platform lander that the rover will need to drive off of.
Okay. What was the other? Oh yeah,
there was a question earlier on from Sarah. This is a more basic question, which again I think is aimed for George. Mars is the red planet, and some planets are ice planets. Io is sulfuric volcanic. The photo of Pluto is fantastic, but I wondered if the red color of Mars and on Pluto is something to do with iron in the soil. So why are Mars and Pluto reddish colored?
Yeah, I can't speak about Pluto, but Mars is, there's iron mixed into the rocks, and over the billions of years that gets eroded away, and it oxidizes, right? So it gets that reddish color, and the erosion of those rocks pulverized into that fine dust that's all over the planet, and it's just been distributed all over the entire planet. That's pretty much why it's all that reddish butterscotchy color. It's very thin. It's very thin coating. You'll see, as particularly when you look at some of the rocks where our descent engines have blown away the surface, you'll see the actual rock itself is a different color because that coating has been wiped away.
Okay. Paul, do you want to put that?
Yes. There was a follow-up question from the question I asked Nick earlier on, from Roger Pittock, saying, Nick, can't you use voting when stacking many images to reject just local areas with satellite trails and increasing the gain where selective parts have been voted off to compensate for the lost data? There's also a comment before you answer that from Roger King saying that Astroart has a line removal tool that works really well to remove Starlink trails. Nick?
I've not heard of a voting system for removing them. Programs like PixInsight do have vertical column removal and replacement, for the column defects on CCDs, but of course the satellites are going to be at all kind of crazy angles. So I hadn't heard of the voting system, and it's something that sounds quite interesting, particularly with the way things are going. So I'll see if I can find some more information about that, because it sounds like it could be quite interesting.
I think it depends very much on the intensity of the line, the satellite trail. One of the problems certainly that has been looked at with the Vera Rubin telescope is the likelihood that the satellite trails will saturate the CCD pixels, because once you've saturated the pixels, you've lost the science, you've lost the data, you've just maxed out the response of the pixels. If you have a fainter streak where you haven't maxed out those pixels, then potentially with some sophistication and looking at the profile of brightness of the streak as it passes across dark areas, you may be able to recover something without completely losing the data underneath. But it's still a little bit like eating a toffee with a wrapper on. It's not quite as good as the original thing.
It may be. I mean, there's some very clever people out there. It may be that because this problem is becoming so sort of prevalent, someone will come up with something that will work in that way, that will allow us to just retain at least some of the sort of science that's in the data, rather than just having to reject it. And again, particularly so for the professionals. So yeah, let's hope that something like that can be developed that filters down to the amateur community as well.
Yes.
And for those who do want more info on astrophotography, Nick, can you remind us where they can get your books and things?
Well, the latest one is just available from Astronomy Now at the moment, just on the website. I don't think it's in the shops at the moment.
And others? I'm just looking through the latest edition which arrived this morning. I know that there's something in there. Ah, right.
Yeah, can't see.
There we
Can't
go.
see it at all, Jerry.
Okay, you should see some of that. So yeah, pick up astronomy.
Thanks,
now.
Joe.
Okay. Right, another question is, how much has NASA explored the geological history of Mars? That should be aerological. So, have any distinctive time periods in Mars history have been identified like they have on Earth?
You're gonna push my scientific knowledge here, but yeah. So there are certain epochs. Maybe I'm using the wrong term, but that the science community have defined that represent the Noachian, Archean, those types of words, terms that define certain different phases of the evolution of Mars, and even those are broken down into other time periods. And in terms of what we've been able to explore, certainly with our orbital fleets over the years, we can look globally and explore different areas that might be based on crater counting and age, that type of relative age dating. Try to analyze from orbit, the morphology of the geology of those areas. But we've had comparatively few, in situ, ground truthing, right? A couple of Vikings, Pathfinder, Spirit and Curiosity. We've had the Phoenix lander up in the North Pole area, and then Curiosity and Insight lander. Although Insight is more looking not at the surface geology, it's the deeper, right, the core of the planet, trying to understand the seismic core, and now Perseverance. So you have to, I guess, do a representative, study of those and then extrapolate. But I saw there was another question of where can you learn more about the geology of the landing sites. Google, geology of Jezero. I think that'll pull up a couple of different, scientific papers. I would expect, I do know our team, one of those slides that I showed showing like the geologic unit map, our scientists, particularly Deputy Project Scientist Katie Stack Morgan, helped laid out a really good map, and Ken Williford, the other deputy scientist, where we are, what type of units we're looking at, and where the team looks like they want to go. So there's definitely a lot out there if you want to learn.
Okay. What's the earliest time scale, someone has asked, for detection of Martian signs of life?
Well, I guess I'll tie that to when we might get our samples home, right? At least for this campaign. Yeah. We're looking to do those return missions towards the end of the 2020s, between 2026 at the earliest, to 28 to launch those. And then the return trip, takes a couple of years. So hopefully we get them back here in the 2030, 31 timeframe. And then of course you got to do the science, right? So sure. It might take another, couple of years to do.
Yes, I mean, they're not going to look down a microscope and say, hey, it's going to take a while. So. That would be great. Oh, well, yes, it would.
But it most likely it would take time.
Yeah. Okay. Someone has said our Astronomer Royal suggests that a robotic exploration of Mars is preferred to human exploration. What are your thoughts?
Sorry, say that one more time.
Sorry. The Astronomer Royal said robotic rather than human exploration is preferable. What are your views?
There's room for both, clearly. Right now it's definitely easier to do robotic exploration of the planets, simply. But we are, at least at NASA, we're working now to try to expand that human capability. We just recently did we're working on what we call the Space Launch System, a new heavy lift vehicle to be able to send humans beyond, moon. The moon is as far as we've sent humans, and we'd like to be able to develop capabilities further. The Orion spacecraft is able to support that. That's also in partnership with, again, shout out to our European partners with that system. And we're looking to do the first demonstrated flight, here in the coming year, uncrewed demonstration of that system, and then looking for crewed next. So, at some point, particularly for Mars, robots are fantastic, but if you could actually have a human crew on the surface, the productivity you could get out of human crews for science is, further beyond what we can do with robotic assets. So, I'd love to see us get to that stage at some point.
And all this takes a huge amount of research and development. Someone has asked, if your mission had failed, would some people then not have received PhD qualifications and so on?
I'm sure a lot of researchers are relying on, if you're a co-investigator or a member of the science team of some of our instruments and you're expecting to get data back, that would probably make that challenging.
Yeah, but then it's the work that you're doing in building up to the mission. That's where all the research is done. So I wouldn't be that hard on people, because we're still learning things whilst doing that.
There's tremendous amount of data to be mined.
Yes,
our orbiting assets there's still tons of, orbit. We've only mapped a very small percentage from orbit in high resolution from the Mars Reconnaissance Orbiter. You've got Trace Gas Orbiter that just arrived, brand new orbiter there from ESA. We've got the Maven Orbiter. We're looking to send some more. We're starting to think about a synthetic aperture radar orbiter with some international partners. So there's always going to be, I think of it like a portfolio approach, right? Maybe yes, you might have some failures here or there, but the overall, our program is meant to be a portfolio of many different missions, types of science, so you can always be making discoveries.
And it is.
If I could just jump in there, Jerry. I'm just going back to George's previous comment. One of the things about sending humans to Mars, of course, is that at the moment we send the robotic missions, and if you lose one, if something goes wrong or it doesn't work properly, it is terrible, and at the very least, it's disheartening. But at the end of the day, it's a machine, and you can build another one, and you can send another one. But pushing the boundary with human lives is potentially much more catastrophic. And I remember back to the days of the shuttle accidents, and then the NASA shuttle program was put on hold for a significant length of time while the wrinkles were ironed out and the investigations were held. And it would be terrible if the momentum of exploration to Mars and the eventual goal of getting people to Mars was put on hold for a significant time, because the attempt was to push the envelope too hard, too early, and put people's lives at risk.
But then, on the other hand, Gus Grissom, one of the Apollo astronauts who died in the Apollo 1 fire, always said, if we die, we want people to accept it. The conquest of space is worth the risk of life. Anyway, moving on, a question about the entry, descent, and landing system, the Sky Crane. Does it use solid or liquid propellants?
That's a liquid propellant.
Yeah.
I think it's a monoprop propellant.
Yes.
Now for the return vehicle, when we do the return lander, there's a trade there. You could potentially use solid. I think that's the way we're headed. That they're still developing that system.
Okay. The major point there is that you don't have to throttle it during flight when you're returning back up from the surface. Mm-hmm. Okay. You mentioned the MOXIE. technology demonstrator, are there any plans to demonstrate processing any other local resources? And the suggestion is here, such as iron, etc., but that's going to take a lot more work.
Well, so, you know, Moxie, again, one of the first demonstrators of, you know, how can we get resources to support future human exploration? The next, you know, being able to generate oxygen out of that's a great resource. We know it's there. You know, carbon dioxide, just split it apart. Yeah. The next resource you really, that's the biggest lever, is water itself. So, you know, and from what we've learned of our orbital assets so far, we believe that there is potentially water ice within the first, you know, few meters of the surface at certain locations. And so that's why one of the next big things to be able to do is, you know, maybe find a way to map that. So that's where this concept of a synthetic aperture radar to do mapping of potential water resources might be. And then you could envision potentially sending a surface mission to go prospect, right? First, you need to do reconnaissance, find out where the resources might be, and then you can do some sort of demonstration or prospecting to see how you might be able to utilize it.
Right, okay. I mean, as a former president of the Mars Society in the UK, this takes me back to Mars Direct and, as you said, in situ resource utilization, where their unmanned return craft would be sent ahead of the crew, land on Mars, and do precisely that, convert the atmosphere into carbon dioxide and oxygen to act as the oxidizer for the liquid hydrogen it would take with them. And together that would provide the fuel for them to return to Earth. So you didn't have to send all of that out to start with. And that was what made the craft capable of being launched on existing technology. And this is something that is not actually new. I mean, this is the Sabatier reaction, which is well over 100 years old. So it's not as though we're going out with untried technology on this, is it? Okay, one other question. Should signs of life be found on Mars, will we be able to determine if it involved independently of life on Earth or if it was due to migration in the past?
Yeah,
wow.
This gets to one of those questions. Yeah. Could you have, you know, during the early period of the solar system when there was more collisions and, you know, early bombardment, things like that, you know, could you have had life that got blasted off from one planet and transmitted to another one? My understanding is that the more likely pathway is for it to come from the outer solar system to the inner. So it might be more likely that Mars came here than the other way around. And of course, we know we have Martian meteorites here on Earth. But, you know, no signs of life in them definitive yet. Yeah, I think that's you know, it's a good question to be asking. Our mission, you know, certainly isn't designed to be able to distinguish. It's going to be looking for very, you know, in situ generated geological formations. You know, definitely, you know, sedimentary rocks and those sorts of things is where we're going to be looking for. So I would expect that whatever we find is going to be native. And that kind of gets to another point. You know, one of the big challenges for Perseverance was to make sure that, since we are looking for these, you know, trying to find signs of Martian life, we had to make sure our spacecraft was ultra clean so that we didn't potentially bring terrestrial life with us and then discover Earth life on Mars, right? That would not help. Yes. So that whole, not only was the sample caching system mechanically complex to do what it needs to do, just the process of making it super clean so that we had confidence that any indications we find is going to be Martian was a huge challenge.
We have another question for Nick. Can you say something about the new CMOS chips that are as quantum efficient as CCD? In particular, is there a DSLR using them that is on sale yet?
Well, I'm probably not the best person to talk to regarding CMOS cameras. I mean, we're aware that the quantum efficiency of the sensors is improving all the time, and certainly the new breed of cameras is, you know, really giving sort of CCDs a run for their money. I don't know. I assume that because the general sensitivity of DSLR cameras, and certainly in terms of their ISO setting, is increasing all the time, the noise levels are going down. I presume that you know, generally CMOS sensors are improving, so we'll see better sensors in DSLRs and presumably camera phones and the like, as well as dedicated astronomical CMOS cameras. Well, the thing that surprises me the most, as someone who's been doing astrophotography right from the earliest days of digital imaging, the short lifespan of the CCD camera. And, you know, I also wonder what professional astronomers will do in the future if a lot of these companies decide to, cease the production of CCD cameras in favor of CMOS sensors, because they're much cheaper to manufacture. So I don't know. I mean, I think it's onwards and upwards for CMOS cameras, and you know, downwards, unfortunately, for CCDs.
Okay.
I think we should be looking at drawing things to a close, Jerry.
To a close soon. Someone's asked, can oxygen be extracted from the rocks of Mars? A lot harder than the MOXIE experiment, of course. But
I have not heard of any concept of how to do that.
Okay. There's just one thing I'd like to come back to about, we were talking earlier about PhD qualifications. When the Huygens craft landed on Titan at the beginning of 2014, John Zarnecki, who was a principal investigator for the surface science package, had mentioned to me that the amount of data that could be transmitted from the surface before the Cassini craft became out of range, it was going to be hidden by the surface of Titan, was the equivalent of about one floppy disk of data. So around 1 meg of data. But he told me PhDs are being written on the strength of that. And he said a few years later, and they are still coming in. It's incredible how much we can interpret from the information that we get back from space missions. And this, of course, only continues to increase. We are, well, we're absolutely overjoyed at seeing Perseverance successfully landing on Mars. We look forward to the flights of Ingenuity and what that will tell and show us as well in the future. Thank you very much, George. Nick, thank you again for your inspiration from the incredible pictures that you provide us, and thanks in their absence to Greg and to Martin for their presentations as well. Paul is going to give say a few notes, and after that I'm going to rerun the sponsors presentations, not just through contractor obligations, but because 2 of them includes offers for you watching this. So over to you, Paul. Okay,
thank you very much, Jerry. And again, echo Jerry's words. Thank you very much to all the speakers. I know Martin, Rees, and Greg Smye-Rumsby aren't here now, but thank you to them, and thank you very much to you, Nick, and to you, George. George in particular must have got up at the early hours of this morning, because when we started at 12 o'clock UK time, it must have been, I think, about 7 a.m. over there in the US, and so it must be very, very wearing on him. So thank you again to all of you. We have coming up at some point, we haven't got a fixed date yet for it. Nick mentioned Telescope Live, and we've managed to work out a deal with Telescope Live for FAS members that will help to allow you to try out Telescope Live. And we're trying to set up a webinar with the Telescope Live people so that they can give tutorials on how to get in and use their system so that you can get the best experience out for your money. Also, in regard to future FAS conventions, we're looking at the possibility of a convention sometime later on this year, depending on how the progress goes with vaccinations and coming out of all this period of lockdown and so on. It may be an in-person convention, but it may also be another online convention. We'll have to see how successful we are with that. That's more or less, I think, all I need to say. So thank you very much for everyone attending, and thank you again to the speakers. I think we've done a really good job today. Just a reminder that yes, Jerry is going to run the two speakers, the two sponsors videos that we couldn't get through, and there are offers in there. So I hope that the rest of you will hang on to hear those. Thank you very much.